A discovery has just been made that defies the normal expectations of celestial behavior. At this very moment in the year 2025, 7 comets are hurtling toward the Sun, all arriving within a span of just a few days in October. Such a phenomenon has never before been documented in human history, making it an extraordinary event that demands our attention. Yet what renders this discovery truly unsettling is not merely its rarity, but the intriguing coincidence that accompanies it. During this same window of time, a peculiar object known as 3I Atlas, an interstellar traveler originating from beyond our solar system, is also approaching its closest point to the Sun. The odds of such a coincidence occurring by chance are astronomically slim, suggesting that perhaps something more complex is at play. Could it be that these arrivals are not simply independent random events? Might they be part of a coordinated sequence, orchestrated by forces beyond our current understanding? Tonight we are embarking on a journey of investigation into every possible explanation, exploring ideas that stretch the boundaries of science as we know it. We will scrutinize whether these phenomena are the result of natural cosmic processes or something more sinister lurking in the shadows of the universe. By the end, we aim to uncover what 3I Atlas is truly doing to our solar system, and whether its presence signifies a deeper, perhaps darker cosmic design. Part 1. A sky filled with cosmic visitors. In an ordinary year, the appearance of one bright comet might be enough to excite astronomers and sky watchers alike. Usually we might see only 1 or 2 such objects that warrant discussion or observation. Most years drift by with little more than faint smudges visible only through telescopes, exciting only the most dedicated comet enthusiasts who spend their nights tracking these distant wanderers. But this year, 2025, feels different. Like the universe itself decided to stage a spectacular parade just for us. It's as if the cosmos has assembled a cast of characters that have caused astronomers around the world to double-check their calculations and question their models. Among these celestial visitors are the comets named Pan-STARRS, Swan, Stereo, Atlas K1, Atlas G3, Lemon, and Neat. Each one is a distinct body carrying within it ice and rock that originated from the farthest reaches of our solar system. Frozen remnants of the primordial material that formed planets eons ago. What makes this lineup extraordinary is not just their diversity, but the timing of their arrival. All 7 are arriving within a few months of each other, as if summoned to a cosmic reunion no one planned or anticipated. To put this in perspective, consider this analogy. Imagine 7 friends from different parts of the country, none aware of the other's plans, all showing up at your house on the same weekend. Each claims ignorance of the other's intentions, possibly even denying any prior arrangement. Is such a coincidence possible? Certainly. Is it likely? Probably not. This scenario raises suspicions. It's reminiscent of what astronomers call a swarm effect, where multiple objects cluster tightly within a short period of observation. From our vantage point on Earth, the pattern looks almost orchestrated, like some unseen hand has herded these bodies together deliberately. This clustering prompts us to ask, could there be a force, a mechanism, or an influence guiding these comets into such a remarkable alignment? Before delving further into this cosmic mystery, let's clarify some key terms that help us understand the phenomena involved. When astronomers refer to perihelion, they mean the point in a comet's orbit when it is nearest to the Sun. At this stage, solar radiation heats the comet's icy nucleus, transforming it from a dormant chunk of ice into a dazzling display of gas and dust tails. What we see is a comet's glorious coma and tail. Closest approach is another important concept. It indicates how near these objects come to Earth, which determines whether we need binoculars, telescopes, or just our naked eyes to observe them. Magnitude is a measure of brightness, an astronomical scale where lower numbers indicate brighter objects. A magnitude of 6 is just barely visible to the naked eye under ideal dark sky conditions, while a magnitude 0 star shines as brightly as the brightest stars in the night sky. Picture a chart that depicts the typical arrival times of comets over many decades. These are scattered across time like raindrops on a window pane, random, unpredictable, and spread out. Now imagine the year 2025. Instead of a few scattered dots, you see 7 dots tightly clustered together, almost as if someone had dropped a handful of marbles onto the timeline. The pattern is unmistakable and immediately stands out. Normally, amateur astronomers spend months, sometimes years, searching the skies for comets worth photographing or tracking. But this year, the abundance and timing of these comets are overwhelming, almost as if the universe has decided to give us a front-row seat to an extraordinary celestial. This year, the skies are offering an unprecedented spectacle, leaving astronomers and sky watchers alike utterly spoiled for choice. Across countless photography forums, vibrant images ripple through digital communities, capturing numerous comet tails streaking across the same patch of the night sky. Meanwhile, social media platforms are flooded with mesmerizing time-lapse videos that appear to depict a meticulously choreographed celestial ballet, an orchestrated dance of cosmic debris moving in harmony, seemingly guided by unseen hands. Yet, as captivating as these visual phenomena are, our investigation takes an unexpected and intriguing turn. While these 7 comets trace their predictable gravitationally governed orbits, each following a path dictated by the well-understood laws of physics, something else stirs in the darkness that exists between the planets. Enter 3, I Atlas, the third confirmed interstellar object ever detected traversing our solar neighborhood. Unlike the familiar comets that originate within our solar system, this visitor was not born here. It was formed around a different star in a distant planetary system, and now, on a solitary hyperbolic trajectory, it is passing through our cosmic backyard only once. The timing of this interstellar visitor's passage raises profound questions that keep astronomers awake at night. Is it merely a coincidence that our solar system's most unusual year for comet activity in recent memory coincides precisely with the arrival of this alien stranger? Or could there be something more deliberate at play, something orchestrated by forces beyond our current scientific understanding? Throughout this exploration, we will maintain a strict division between what can be measured and verified and what remains speculative. When discussing orbital parameters, observation logs, and brightness data, you can rely on the accuracy of those numbers. Conversely, when we delve into possibilities that extend beyond established science, hypotheses about unseen influences or unknown forces, we will clearly mark them as speculative. Our approach is not about pushing unproven theories, but about pursuing the evidence wherever it may lead. The criteria for our investigation are simple yet rigorous. If 3I Atlas is indeed linked to the swarm of comets, if a connection exists, it should leave behind unmistakable signatures. These might include timing correlations that surpass what is statistically probable, orbital relationships that cannot be dismissed as coincidence, or measurable physical interactions that can be verified through observation. We are not seeking vague hints or patterns open to creative interpretation. Rather, we are hunting for concrete, quantifiable evidence, data robust enough to convince even the most skeptical astronomer, that would elevate speculation into established scientific fact. The stakes of this inquiry extend well beyond mere academic curiosity. Should these comets have arrived independently, following only the random yet predictable rules of orbital mechanics and the discoveries of survey telescopes, then what we are witnessing is a remarkable but ultimately natural celestial coincidence. The universe's vastness makes such clustering possible. Occasions where objects seem to converge in a way that feels meaningful but is simply a product of chance. These are the moments when we observe a pattern, but one that the universe's size and randomness can produce without any deeper significance. However, if some external influence, whether gravitational, electromagnetic, or something entirely unknown, has nudged these objects toward a synchronized arrival, then we are confronting evidence of forces operating on scales and in manners that challenge our current scientific paradigm. Such forces could fundamentally reshape our understanding of how objects move and interact through space. Consider what this would imply. 7 comets don't just happen to converge without reason in the vastness of space. In a solar system governed by deterministic laws, every orbit is a story written by the forces that shaped it. Each trajectory carries within it the fingerprints of the gravitational, electromagnetic, or perhaps even yet undiscovered influences that have guided its path. The implications are profound. If external forces have indeed influenced these objects' journeys, it suggests a level of cosmic orchestration, an unseen hand that could alter the way we comprehend the mechanics of our solar system and the universe at large. Every orbit, every path taken by a celestial body is a silent narrative of its history and the forces that have shaped it. Discovering a deviation from the expected, an external influence, would open new avenues of scientific inquiry, forcing us to reconsider the boundaries of our current models and perhaps hinting at phenomena we have yet to conceive. If some unseen force had a hand in guiding these celestial objects along their current trajectories, then unmistakable traces, like fingerprints, should be detectable through careful analysis. The presence of an interstellar visitor introduces yet another layer of profound mystery into this cosmic puzzle. Known as 3I Atlas, this object carries within it ice and dust forged in the intense fires surrounding a distant star, its very composition seasoned by cosmic radiation during what was likely a journey spanning millions of years across the vast expanses of interstellar space. These chemical signatures serve as invaluable clues, revealing secrets about planetary formation processes in other stellar systems far beyond our own. As it approaches our Sun, the behavior of this interstellar traveler offers further insights. How materials from elsewhere respond when subjected to stellar heat, shedding light on the nature of extraterrestrial matter that has traveled across the galaxy. But what if its arrival was not merely a matter of cosmic happenstance? Could the same unseen force that may have herded 7 comets originating within our solar system into a synchronized arrival also have guided this interstellar visitor toward us at precisely the right moment? Such a hypothesis raises questions that multiply like fractals, patterns within patterns, each answer spawning a host of new mysteries. How could we even detect such an influence? What mechanisms could operate across the immense distances of space to coordinate objects with such astonishing precision? And if such coordination is indeed possible, what implications would that have for our understanding of the true nature of our cosmic neighborhood, the fabric of the universe itself? As we prepare to scrutinize each member of this extraordinary cast, the 7 seemingly unrelated comets, we must remember that the universe rarely yields its secrets without a struggle. Every significant discovery begins with an observation that doesn't quite fit the expected pattern, a clue that challenges our preconceived notions. Every breakthrough starts with someone asking, "Why isn't this as simple as it appears?" The celestial swarm has arrived, bringing with it questions that could shake the foundations of everything we think we know about the dynamics of our solar system. But before jumping to conclusions, we must first meet these 7 visitors properly, seeking to understand what makes each one unique. Are these coincidences, or are they signs of a deeper connection? The evidence is waiting to be uncovered, and the time has come to start measuring, analyzing, and interpreting. Let's begin with part 2 of this investigation, the roll call of the swarm. We will examine each of our 7 visitors individually because each carries its own story of discovery and a cosmic journey that has led it to our skies. Imagine a lineup where every suspect has an alibi, yet somehow they all end up at the same crime scene. The first star of this celestial parade is Pan-STARRS, taking center stage as our initial and most luminous performer. Discovered by the Panoramic Survey Telescope and Rapid Response System, a revolutionary sky patrol based in Hawaii, this instrument has transformed the art of comet hunting. Pan-STARRS stands poised to reach naked-eye visibility for observers in the Northern Hemisphere, with its approach window spanning from late March to May of the year 2025, giving astronomers months to study its behavior as it nears. What makes Pan-STARRS particularly intriguing isn't solely its potential for brightness, but also its orbital geometry. Its path brings it relatively close to Earth's orbital plane, making it readily visible from populated latitudes across the northern continents. For those pattern seekers among us, this convenient accessibility might seem almost too perfect. Perhaps some might wonder, is it merely a coincidence that such an object appears so well positioned, especially if we accept the notion that it wandered in from the distant outer reaches of the Oort cloud entirely by chance? The odds seem slim. Next in our lineup is SWAN, which presents an entirely different story of discovery. The spacecraft Solar Wind and Isotropies, designed primarily to study solar particle streams, unexpectedly became a comet hunter when its hydrogen detection instruments began to pick up the characteristic glow of a comet's atmosphere. This serendipitous detection revealed the presence of a cometary body, a discovery that underscores how sometimes the universe whispers its secrets in unexpected ways. SWAN's appearance with its sudden outgassing activity hints at a level of preparedness, remarkably active for a comet that supposedly arrived from the outermost regions of the solar system's distant periphery. Its hydrogen emissions tell us that it was already shedding material into space months, perhaps even years, before it was officially identified, adding another piece to this cosmic puzzle. Together, these observations, each from different detection methods and instruments, compose a mosaic that hints at an underlying pattern. The question remains, are these just chance coincidences, or do they point towards an unseen orchestrating force? As we proceed, each new discovery will deepen our understanding or further complicate the puzzle, compelling us to consider possibilities that stretch the limits of current scientific understanding. SWAN comets often manifest suddenly within the data streams, their presence heralded by distinctive hydrogen emissions that precede the capabilities of optical telescopes to detect them. This spectral signature of hydrogen is more than just a fleeting detail. It provides crucial insight into SWAN's current activity level. Unlike inert rocks that only brighten as a result of solar heating awakening dormant surfaces, SWAN was already actively outgassing at the moment of its discovery. For months, perhaps even years, it has been shedding material, forming that unmistakable hydrogen envelope that betrayed its location long before optical observations could confirm it. What makes this particularly intriguing is the apparent preparedness of SWAN for its solar system debut, despite the claim that it was following a seemingly random orbit. Its early activity suggests a level of readiness that raises eyebrows, almost as if it knew or was somehow guided to be active at just the right moment. Turning to Stereo, the Solar Terrestrial Relations Observatory, we find perhaps the most compelling and dramatic account of a celestial visitor. Positioned strategically to monitor the sun's activity, Stereo spacecraft often catch fleeting glimpses of objects racing toward or near our star in their peripheral vision. These comets, observed in the outer regions of the solar system, sometimes become suicidal grazers, hurtling so close to the sun that they disintegrate in spectacular, often fiery fashion. Alternatively, they emerge from this perilous encounter fundamentally transformed, their structure and appearance altered by the intense solar environment. The timing of Stereo's discovery in particular warrants careful attention. Remarkably, Stereo's detected comet arrived during a period of heightened solar activity, when our star's magnetic field was especially turbulent and its solar storms more frequent and intense. Is this merely coincidence? Or does the solar maximum, characterized by maximum magnetic chaos, somehow create conditions that actively draw objects from the distant reaches of the solar system inward? The correlation between solar maximum conditions and the inward journey of these comets feels too precise, too consistent to dismiss outright. The possibility that solar activity itself might influence or even trigger the inward migration of cometary bodies prompts questions about the underlying mechanisms at play. Turning to Atlas K1, we find a case shrouded in the duality of astronomical hype and subsequent disappointment. When the asteroid terrestrial impact last alert system first detected this object, early predictions of its brightness suggested it might become one of the most spectacular comets seen in decades. A truly remarkable visitor. Yet, as often happens, reality proved more modest. Atlas K1, while still visible with binoculars or a small telescope, fell short of the dramatic spectacle initially anticipated. What makes Atlas K1 suspicious in the context of this investigation is its timing. Its discovery date falls squarely within the same broad timeline as the swarm of comets, yet its orbital characteristics suggest it has been following this particular path for thousands of years. Why are we only detecting it now? Why this year precisely when 6 other comets are also arriving within the same narrow observational window? The coincidence of multiple bodies appearing simultaneously, despite their long independent histories, raises questions about whether some external factor or unseen influence might be at work. Atlas G3, sharing the same survey heritage as its K1 sibling, further complicates the picture. Both were discovered by the same Hawaiian telescope system, which has become highly efficient at detecting potentially hazardous objects. This system operates like a cosmic early warning network, scanning the entire visible sky every few nights and carefully tracking any object that moves against the background of stars. What troubles careful observers, however, is that many recent comet discoveries trace back predominantly to Atlas operations, not because the system is flawed, but because it is exceptionally advanced. This technological prowess allows for the detection of faint objects that previous surveys might have missed. Yet when multiple members of an unusual swarm are identified by the same survey system within a short time frame, a pattern begins to emerge, demanding explanation rather than mere coincidence. Adding another piece to this cosmic puzzle is Comet Lemon, which introduces a different pedigree to our gathering. Discovered by the Catalina Sky Survey Station located on Mount Lemmon in Arizona, Lemon has been part of the hunt for near-Earth objects since the 1990s. Over the decades, this survey has accumulated one of the most comprehensive databases of small bodies within our solar system, providing critical orbital data and tracking history. The significance of Lemon's discovery lies not only in its pedigree but also in its positioning within the swarm. It arrives neither at the forefront nor at the tail end of the group, but rather in the middle, maintaining a formation that, at first glance, seems mathematically precise. This arrangement appears unlikely to be purely the result of random orbital evolution, further fueling suspicion about potential underlying influences guiding these bodies into a seemingly coordinated appearance. Together, these observations, ranging from Swan's sudden outgassing signatures to Stereo's dramatic solar encounters and Atlas's suspicious timing, compose a complex narrative. They prompt us to consider whether the apparent coincidence of multiple comets arriving simultaneously is a natural, The discoveries surrounding Lemon carry the weight of decades of meticulous observation and precise orbital calculations. Its visual presence in the night sky remains modest, likely only observable with binoculars at best. Yet its placement within our swarm sequence is precisely what renders it so intriguing. Lemon arrives roughly in the middle of the group, neither at the forefront nor trailing behind. Instead, it sits as a kind of cosmic placeholder. Its position is maintained with an extraordinary mathematical accuracy that seems improbable to have arisen from purely random orbital mechanics. This deliberate arrangement, with Lemon nestled amidst other comets, adds a layer of mystery that beckons further inquiry. Adding to the narrative's irony is how it completes our septet of celestial visitors. The Near-Earth Asteroid Tracking Program, which ceased operations in 2007, originally aimed to identify potentially hazardous objects approaching our planet. Remarkably, the comet discoveries made during its active years continue to arrive in predictable patterns, following orbits calculated decades ago. These comets serve as enduring legacies of systematic sky surveys, proof that diligent, patient observation eventually yields tangible results. What makes Nietzsche's participation in this swarm particularly notable is the significant time delay between its initial discovery and its arrival. This comet has been tracked with great precision for over 15 years, with its orbit refined through thousands of observations. There is now no uncertainty about its trajectory. Its path and timing are firmly established. Nietzsche was always destined to arrive in the year 2025, its journey meticulously mapped long ago. So the real question that lingers is, why is Nietzsche arriving alongside 6 other comets? When we plot all 7 orbits on a single timeline, the clustering of their arrivals becomes impossible to ignore. These are not objects discovered in recent years that just happen to be visible now. Instead, they are comets uncovered across different periods by different surveys employing various detection methods, yet all converging on this remarkably narrow window in time. The diversity of how and when these comets were discovered only amplifies the improbability of this coincidence. Hydrogen emission detections, solar observation data, asteroid survey records, and dedicated comet hunting expeditions all contributed different pieces to this complex puzzle. It's as if the universe deliberately scattered clues across multiple detection techniques, ensuring that we would eventually recognize this unusual pattern. Now consider the statistical improbability of such an event. Comet discoveries tend to follow a roughly random distribution over time, with occasional minor clusters that rarely exceed 2 or 3 objects. The arrival of 7 comets within a span of months stands out as a clear outlier, an anomaly that demands explanation. Yet here they are, each following orbital paths calculated with a precision rooted solely in gravitational physics. Paths set millions of years ago when these 7 visitors embarked on their long, slow journey toward the inner solar system. This raises a haunting question for every diligent observer. What underlying force could have set these paths in motion with such an apparent degree of coordination? What mechanism operating across the vast distances and immense timescales of the outer solar system could have nudged multiple objects into synchronized, near-simultaneous arrivals? It's important to clarify that we are not asserting that these comets are part of a coordinated effort. Instead, we are simply documenting a pattern, one that appears so striking that it warrants serious investigation. While each individual comet adheres to the natural laws of motion, laws that are well understood and predictable, the collective behavior of this swarm suggests something beyond mere coincidence. It hints at an underlying influence or force that might be operating on a scale and in a manner we have yet to comprehend. In essence, we are observing a pattern that, while consistent with natural physics, appears too precise and too improbable to be purely accidental. The question of what set these paths in motion remains open, but the pattern itself compels us to look deeper, to consider whether an unseen force, be it gravitational, electromagnetic, or something entirely unknown, could be responsible for this remarkable synchronization. Before we can even begin to consider any potential link between our peculiar interstellar visitor and the unusual clustering of comets, it is crucial to understand why such a concentration of cometary activity in a single year feels so extraordinary to seasoned astronomers. To do this, we need to explore what a typical year in comet observation actually looks like, a baseline against which anomalies can be measured. This leads us into the realm of why this situation diverges markedly from the norm, which is the focus of the third part of our investigation. Why this is not normal. Imagine stepping into any planetarium on an ordinary year and posing a simple question. Are there any visible comets this year? The response from the astronomer might be a resigned sigh, followed by a quick check of their extensive database. They might then mention one or two marginal objects, faint, elusive, and requiring a good telescope, dark skies, and patience to observe. Sometimes, if luck is on your side, there might be a comet bright enough to be seen with binoculars. Yet even then, it's often a challenge for dedicated enthusiasts to track it down. For most years, the sky remains largely devoid of spectacular comet displays, with perhaps a handful of faint smudges glimpsed through telescopes. This is the reality most observers accept: patient waiting, occasional disappointment, and fleeting rewards that demand serious equipment and expertise to appreciate fully. Meanwhile, the general public remains largely unaware of these faint, fuzzy patches. Things that excite only amateur astronomers and sky watchers, those willing to sift through the night's darkness to find these celestial visitors. For most people, comets exist only in the pages of history books or in dramatic scenes in disaster movies. Rare, distant, and often used as symbols of impending change or catastrophe. Then comes the year 2025. It dramatically shatters this silent, predictable pattern with the force of a cosmic sledgehammer. Instead of one or two faint visitors, the year witnesses the appearance of 7 notable comets within just a few months. An extraordinary cluster that feels almost surreal in its improbability. Multiple objects become bright enough to photograph with ordinary cameras, turning the night sky into a celestial parade. Several of these comets reach binocular visibility, and at least one promises a naked-eye spectacle, an event that even casual observers could enjoy if they happened to look up at the right moment. To truly grasp how exceptional this clustering is, we must understand the mathematics behind comet discovery and visibility, an area where modern sky surveys have fundamentally transformed our capabilities. These surveys have revolutionized our ability to detect distant, faint objects in the solar system, but they haven't altered the basic physics that determines when a comet becomes bright enough for us to notice. For example, the Panoramic Survey Telescope and Rapid Response System based at Hawaii's Haleakala Observatory scan the entire available sky every few nights, hunting for moving objects. Similarly, the Catalina Sky Survey in Arizona systematically covers different patches of the sky with high precision, while space-based infrared telescopes like NEOWISE detect the heat signatures of objects that are otherwise hidden from view. All these programs combined discover hundreds of new comets and asteroids annually. Yet the vast majority of these objects remain faint, detectable only through telescopes, never bright enough to catch the public's eye or even be seen with binoculars. Statistically, the expected number of comets in any given year that reach naked-eye brightness is between 0 and 1, with perhaps 2 or 3 additional comets becoming accessible to serious amateur observers. This is a pattern that has persisted over decades, an essentially steady background against which the 2025 anomaly stands out like a glaring outlier. Importantly, this unusual abundance cannot be explained away simply by the improved detection capabilities. While our telescopes now find more objects overall, more distant, fainter, and harder to see, the percentage of these objects that brighten into notable comets remains consistent with historical patterns. The increased sensitivity of modern instruments does not magically produce bright comets where none existed before. It merely reveals more faint objects. The intrinsic properties that determine a comet's brightness, its size, its chemical makeup, and its proximity to the Sun during its closest approach, are set long before discovery, often millions of years ago when gravitational perturbations first nudged these objects from the outer reaches of the solar system toward the inner regions. In essence, the visibility of a comet is rooted in its inherent characteristics. The brightness we observe depends on how large the comet is, what materials it is composed of, and how close it gets to the Sun at perihelion. These attributes are fossil records of its formation, preserved through eons, and largely unaffected by how advanced our detection technology has become. What makes the Dve-Tisici-Dvacet-Pat cluster so extraordinary is that it defies the natural statistical expectations based on these physical parameters. Instead of a random, dispersed distribution of comet appearances over time, we see a remarkable concentration, a cosmic coincidence that warrants careful scrutiny. In summary, while our evolving observational tools can reveal more faint objects than the capabilities of modern sky surveys have revolutionized our ability to detect celestial objects, yet their role is often misunderstood. These surveys don't necessarily discover more bright comets because the universe is suddenly producing an increased number. Rather, they identify objects that were already destined to appear. The enhanced detection tools simply reveal what was always going to be observable. These comets' arrival in 2025 was inevitable long before our current technology improved. This distinction holds profound significance for our investigation. If the clustering of comets in 2025 were merely a product of improved survey capabilities, then similar patterns should have appeared in other recent years as telescopes and detectors became more advanced. Instead, what we observe is an extraordinary anomaly. The year 2025 stands alone as a remarkable concentration of cometary activity, unlike any other recent period. This singularity prompts a careful reconsideration of what we're seeing, especially because media coverage often amplifies modest objects, those barely visible or faint, into spectacular events, raising public expectations and sometimes leading to disappointment when the actual brightness falls short of sensationalized reports. Understanding the brightness of comets involves the magnitude scale, which operates inversely. The lower the number, the brighter the object. For example, a magnitude of 6 marks the approximate limit of naked eye visibility under pristine dark sky conditions. Most suburban observers with their limited light pollution typically need binoculars to see anything dimmer than about magnitude 4. Predicting comet brightness is notoriously uncertain because it depends heavily on outgassing rates, how volatile materials vaporize, and on how solar heating interacts with the comet's composition. These factors are complex and resist precise calculation, making accurate predictions challenging. A comet's brightness can change dramatically depending on internal and external conditions. If it contains volatile substances that vaporize suddenly, it might brighten unexpectedly, creating a dazzling display. Conversely, if its surface develops an insulating crust of dust, activity can become suppressed, leaving the comet dimmer than anticipated. Despite these uncertainties, veteran comet observers develop a refined intuition over decades, enabling them to distinguish objects likely to produce spectacular displays from those destined to remain modest. When experienced astronomers express surprise at how crowded the comet calendar appears in 2025, Their reactions carry considerable weight, stemming from long-standing familiarity with the faint and unremarkable objects that fill the skies in typical years. Adding another layer of complexity to this unusual year is the connection to solar activity, which follows an 11-year cycle. The sun periodically shifts from periods of relative calm with few sunspots to active phases characterized by frequent solar flares and coronal mass ejections. The year 2025 coincides precisely with the solar maximum, the peak of this cycle, when the sun's magnetic field is at its most turbulent. During solar maximum, the enhanced solar wind, a stream of charged particles, can dramatically influence the appearance and behavior of comets. These space weather events can produce spectacular tail phenomena, such as tail disconnection events or unusual tail geometries, which can make modest comets seem far more active or brighter than their intrinsic properties would suggest. Furthermore, the heightened solar wind during maximum amplifies ion tails, potentially rendering the 7 visitors more photogenic, more likely to produce striking images than they would during quieter periods at solar minimum. Importantly, however, solar activity does not generate comets. It only affects how they look once they arrive in the inner solar system. The objects destined to approach Earth in 2025 had already been set on their paths, regardless of whether the sun was active or calm. Solar maximum might enhance observational spectacle, but it does not provide an explanation for why 7 different comets chose this specific year for their close encounters. This is where human psychology complicates our objective understanding. Our brains are hardwired to find patterns. Evolution favored pattern recognition because missing genuine patterns could have been fatal in ancient environments, such as missing the signs of predators or natural disasters. Consequently, we tend to see connections and regularities even where none exist, especially in complex data sets or seemingly coincidental events. This ingrained tendency to detect meaningful patterns in randomness leads us to interpret the clustering of comets in 2025 as possibly more than just a statistical anomaly, prompting biases that can influence our perception and judgment. Our innate pattern recognition ability has served us well across countless scenarios, enabling us to detect order amid chaos and find meaning where there might be none. This remarkable skill, however, can also mislead us into perceiving connections that do not truly exist. When events cluster together, they naturally catch our attention and compel us to seek explanations, often assuming an underlying cause rather than dismissing the coincidence as mere chance. This cognitive bias becomes particularly potent when the events appear to be coordinated or intentionally purposeful, triggering our instinct to interpret patterns as signs of some hidden force at work. The recent phenomenon of the 7 comets arriving within a span of just a few months exemplifies exactly this kind of pattern-seeking response. To our intuition, 7 objects appearing in close temporal proximity seems far too orderly to be the product of random processes. It feels orchestrated, almost deliberate. Our subconscious resists accepting such a clustering as a coincidence because it conflicts with our sense of probability and randomness. Yet, when we turn to rigorous statistical analysis, the picture changes. It reveals that clusters of events, sometimes seemingly improbable, are not only possible but occur regularly in purely random distributions. For instance, if you flip a coin enough times, inevitably you'll encounter long streaks of heads or tails that seem extraordinary but are, in fact, the natural consequence of chance. This disconnect between intuition and statistical reality presents a challenge. Our minds struggle to accept that seemingly unlikely clusters can arise from randomness without external influence. The core difficulty for our investigation is distinguishing between genuine statistical anomalies, patterns that genuinely suggest some underlying cause, and those that are simply the product of chance, falling within the spectrum of normal variation. To make this distinction, we need measurable, objective criteria that can tell us when a pattern surpasses the limits of reasonable coincidence. This is where detailed orbital analysis becomes indispensable. If these 7 comets share subtle gravitational influences, such as similar source regions, common source objects, or synchronized perturbations, it might indicate some external force or influence guiding their paths, one that exceeds what random chance would produce. Such evidence would lend weight to the hypothesis of external coordination or herding. Conversely, if their apparent clustering can be explained by the natural variability of orbital mechanics, statistical fluctuations, and the vastness of the data set, then coincidence remains the most plausible explanation. To reach a sound conclusion, the evidentiary bar must be set high. Extraordinary claims, especially those proposing some unseen force manipulating celestial objects, demand extraordinary proof. The assertion that a force managed to herd 7 comets into a near-simultaneous arrival qualifies as an extraordinary claim, requiring detection signatures that could convincingly sway skeptical astronomers, experts adept at debunking false correlations and spurious data. We must seek measurable objective indicators, orbital signatures, synchronized perturbations, or behavioral anomalies that cannot be explained by random chance alone. As we prepare to explore potential mechanisms that might produce such coordination, it is essential to remember that the universe occasionally surprises us with phenomena that defy our current understanding. Sometimes the seemingly improbable explanation turns out to be true. Other times, coincidences conceal deeper truths, waiting patiently for meticulous investigation to uncover them. The swarm of comets is undeniably real, their timing strikingly unusual, and the questions they pose demand rigorous answers. But this leads us to a profound puzzle. What force or mechanism could possibly coordinate objects across such vast distances and enormous timescales? Could our interstellar visitor, the one traveling through our solar system from beyond, be the missing piece, perhaps even a catalyst or messenger in this cosmic puzzle? Part 4 invites us to consider an intriguing possibility: the unseen hand. When astronomers encounter patterns that seem inexplicable, their primary explanations typically revolve around 2 fundamental forces: gravity and electromagnetism, forces that govern almost everything in the cosmos. Gravity orchestrates planetary orbits and the trajectories of celestial objects, while electromagnetic forces influence charged particles, shape comet tails, and drive various space phenomena. Exploring these forces helps us understand whether the observed clustering could stem from natural physical causes or if other, more mysterious influences are at play. If an external influence is somehow orchestrating the synchronized arrival of 7 comets, it must be operating through one of the fundamental forces that govern celestial motion. Let's begin with gravity, the reigning master of cosmic choreography within our solar system. Every object possessing mass warps the fabric of space-time around it, creating an invisible yet precise architecture, an intricate gravitational framework that directs the paths of planets, asteroids, and comets alike. Gravity's reach extends across vast interplanetary distances with a mathematical accuracy that allows astronomers to forecast celestial events centuries into the future. Its laws are well understood and remarkably predictable. However, the key limitation of gravity must be emphasized: it is inherently a weak force. To produce effects that are noticeable across the immense stretches between objects in our solar system, a mass of significant magnitude is required, something comparable to a planet or a large moon. The Sun, by virtue of its overwhelming gravitational dominance, shapes the broad, overarching patterns of planetary and cometary motion. Jupiter, although only about 1,000th the Sun's mass, exerts a formidable gravitational influence, sculpting gaps in the asteroid belt, capturing Trojan companions that orbit alongside it, and redirecting countless comets through close encounters. For an unknown object to be actively shepherding 7 comets into such a tightly synchronized cluster of arrivals, it would need to possess a mass comparable to a major planet. An object with a gravitational pull strong enough to alter orbits on a significant scale. We are not talking about subtle nudges that accumulate over millions of years. We're discussing a force powerful enough to produce immediate measurable orbital perturbations. Such an influence would be unmistakable to any orbital analysis, with signatures that are impossible to conceal or disguise. The orbital elements of comets, parameters such as inclination, eccentricity, and the timing of perihelion, are direct fingerprints of the gravitational influences they have experienced during their journeys. These signatures serve as a celestial record revealing the unseen hands that have shaped their paths. If some massive yet hidden object has been exerting control over these 7 visitors, its presence would be encoded in their orbital characteristics, an unmistakable pattern of perturbations or shared gravitational signatures. Astrophysicists have a well-established template for detecting such covert shepherding. Jupiter itself exemplifies how real gravitational influence operates. It has carved out gaps in the asteroid belt, captured groups of Trojan asteroids that share its orbit, and repeatedly redirected comets through gravitational encounters. These effects are measured with extraordinary precision, allowing scientists to calculate the forces responsible and to predict future interactions confidently. Applying this understanding, if an unseen massive object is responsible for orchestrating the swarm, we should observe consistent anomalies, perturbations, synchronized shifts in orbital elements, or other signs of shared influence, indicating a common source. The absence of such signatures, however, would strongly suggest that no gravitational shepherding, no hidden planetary or planetary-like mass, is at work. Without detectable perturbations, the idea of a covert, gravitationally influential object guiding these comets becomes exceedingly unlikely. Now, turning to electromagnetic influences, these forces operate under a different set of constraints but are no less precise. Comets, after all, carry electric charges, an effect induced by solar radiation ionizing their gas clouds. These charged particles respond to magnetic fields in ways that are measurable. The solar wind, a constant stream of charged particles flowing outward from our star, shapes the ion tails of comets and can induce dramatic disconnection events during magnetic storms. Such interactions are well documented and observable. Yet electromagnetic forces differ fundamentally from gravity in their mode of action. They predominantly influence the comet's tail and atmospheric behavior, affecting the visible and gaseous features rather than the actual orbital trajectory. While solar magnetic activity can cause tails to twist, kink, or even disconnect, it does not significantly alter a comet's path through space. The comet's orbit remains largely governed by gravitational laws, with electromagnetic effects playing a secondary surface-level role. In summary, if a mysterious force is orchestrating these comets' synchronized arrival, it would need to operate through mechanisms capable of exerting influence at a distance, be it gravitational or electromagnetic. The evidence, or lack thereof, of orbital perturbations and shared gravitational signatures serves as the critical test. So far, detailed analyses show that each comet's orbital parameters are consistent with independent natural evolution under known physics. No shared anomalies or perturbations suggest a hidden shepherd in the form of an unseen planet or massive object exerting a coordinated influence. Similarly, electromagnetic effects, while influential on comet tails, do not explain alterations in their fundamental orbits. Thus, the simplest explanation remains. These comets are arriving in a pattern consistent with chance, natural orbital dynamics, and the statistical clustering of discoveries, an unremarkable yet extraordinary celestial coincidence. A comet's tail may twist and dance in response to the dynamic fluctuations of solar magnetic activity, yet the comet itself relentlessly persists on its trajectory, governed by the immutable laws of gravity with unwavering precision. The notion that electromagnetic fields could be manipulated to steer 7 different comets into a synchronized arrival, appearing as if coordinated, is fundamentally challenged by the laws of physics as we understand them. To achieve such steering through magnetic influence, fields would need to be vastly stronger than any magnetic phenomena observed within our solar system, with energy demands that would easily surpass the entire output of our sun's emissions. We're talking about forces typically associated only with the vicinity of neutron stars or black holes, extreme environments far beyond the realm of planetary or solar magnetic activity. Furthermore, if such electromagnetic manipulation were truly occurring, it would leave unmistakable signatures in the spectral data and tail behavior of these comets, signatures that would be impossible to conceal from diligent observatories. Every telescope, spectrometer, and camera studying these objects would immediately detect telltale signs of external influence. This realization leads us to the crucial criteria that distinguish genuine scientific evidence from mere speculation. Authentic shepherding, whether through gravity or electromagnetic forces, must produce observable effects that withstand the most rigorous scrutiny. First, the affected objects should share orbital elements, parameters such as inclination, eccentricity, and perihelion, that suggest a common influence rather than independent random paths. Second, their trajectories should exhibit consistent perturbations, small but measurable deviations, that cannot be explained solely by gravitational interactions or measurement uncertainties. Third, there should be synchronized anomalies, behavioral or positional changes, that are statistically improbable to result from pure chance or independent evolution. Applying these stringent criteria to our collection of 7 comets, Pan-STARRS, Swan, Stereo, Atlas K1, Atlas G3, Lemon, and Nichir, systematically reveals the picture. Do their orbital characteristics hint at a shared influence? The preliminary answer is disappointingly clear: they do not. Instead, each comet's path appears to be the product of natural independent evolution under the well-understood influences of gravity, with no evidence of external shepherding. Their origin regions, orbital inclinations, and the timing of their approaches all align with what we would expect from random clustering, statistical flukes that can naturally occur in a vast cosmos. For example, Pan-STARRS approaches from a different direction than Swan, whose trajectory is markedly distinct from Stereo's solar grazing path. Atlas K1's orbit, more distant and elongated, bears no resemblance to Atlas G3, which was detected in a different part of the sky. Lemon and Nichir, originating from separate zones of the outer solar system, have traveled along entirely different routes en route to their current positions. If some unseen force or intelligence were actively orchestrating these arrivals, we would expect to see subtle but significant correlations, such as orbital elements that align more closely than chance would allow, recurring nodes where their paths intersect, or perturbations that suggest a common origin. We would observe timing relationships that defy statistical probability, indicating an influence beyond natural gravitational or solar effects. Instead, the data shows quite the opposite. These 7 objects are following their own independent journeys. Each trajectory reflects a history of isolated natural evolution, shaped by the predictable gravitational tug of the sun and by occasional encounters with planets or asteroid belts. Their paths only converge in the sense that they all happen to reach their maximum brightness during roughly the same period, an apparent clustering that can be attributed to statistical chance rather than deliberate coordination. In essence, their orbital stories are those of solitary travelers, each with its own origin point, journey, and orbital evolution, rather than members of a coordinated fleet. The evidence strongly supports the conclusion that the forces guiding these comets are consistent with established physics. There is no compelling reason based on current observational data to invoke unseen shepherds, magnetic controllers, or extraterrestrial puppeteers. The natural independent evolution of their orbits remains the most parsimonious explanation for their apparent clustering. While the idea of external coordination cannot be entirely dismissed, it does set a much higher standard of evidence before it can be considered credible. If there is some force or influence affecting these comets, it must be operating through mechanisms so subtle and elusive that our current observational tools are insufficient to detect them. The most straightforward explanation, supported by the available evidence, remains that of statistical clustering, an outcome amplified by the advancements in survey technologies and detection capabilities. Such natural patterns, although remarkable, are still consistent with the known laws of physics and the random nature of celestial mechanics. However, the investigation takes an intriguing and provocative turn when we consider the possibility of the interstellar object known as 3I Atlas, acting as a potential coordinator in this cosmic dance. Unlike the 7 comets that originate within our solar system, this interstellar visitor bears no allegiance to the gravitational patterns that govern native objects. Its hyperbolic trajectory, an unmistakable sign of its external interstellar origin, makes it a genuinely foreign presence in our celestial neighborhood. This raises an unsettling question. Could such an object, despite its relatively small mass, exert some influence, perhaps through mechanisms we have yet to fully comprehend, on the timing or behavior of our native comets? This question pushes the boundaries of our current understanding of physics, venturing into territory that challenges conventional models. Yet, given the unusual circumstances surrounding this year's comet swarm and the arrival of 3I Atlas, it warrants serious consideration. The limitations of 3I Atlas as a shepherd are immediately apparent. Its estimated mass is far below that of any planet, rendering its gravitational influence effectively negligible. Its swift passage through the solar system also leaves a very narrow window for any subtle perturbations to build up or manifest. Additionally, its trajectory does not intersect directly with any of the 7 native comets, which makes close gravitational encounters or direct influences highly unlikely. Despite these facts, the persistent coincidence of timing remains a source of concern for those who prefer a universe free of mysterious correlations. The arrival of an interstellar object during what is arguably the most active comet year in recent memory seems too convenient to be mere coincidence. Even if 3I Atlas cannot exert a direct gravitational influence, could its presence, perhaps as a catalyst or a signal, correlate with conditions that increase the likelihood of comet clustering? Might its appearance be an indicator rather than a cause of broader natural processes or environmental conditions within the outer solar system? This question opens a fascinating realm of speculation grounded in observational constraints. We are not suggesting the existence of invisible tractor beams or exotic physics that would violate the established laws of nature. Instead, we are exploring whether the arrival of an interstellar visitor might coincide with, or even signal, natural processes that enhance comet activity or detection rates. Perhaps, in a broader sense, 3I Atlas serves as a cosmic weather vane, marking periods when the outer solar system experiences heightened gravitational stirring or other dynamic phenomena that increase the rate at which comets are nudged sunward. The hypothesis that interstellar visitors might preferentially arrive during such periods is intriguing. It suggests a form of cosmic synchronization, where the influx of interstellar objects aligns with times of increased celestial activity, potentially due to underlying gravitational perturbations or other natural mechanisms. These possibilities, while requiring rigorous investigation, could explain how seemingly improbable coordination might naturally emerge from processes operating on scales and in environments we are only beginning to understand. Such subtle connections and correlations are not without precedent in cosmology and astronomy. The universe has a history of revealing surprising links, initially dismissed as coincidence, that later become foundational insights into the workings of cosmic phenomena. As our observational tools and theoretical frameworks continue to improve, what now appears as an improbable coincidence might, in time, be understood as a piece of a far larger and more intricate cosmic puzzle. As we prepare to confront our interstellar suspect directly, it's important to remember that the most groundbreaking discoveries often originate from observations that defy standard explanations. Sometimes what appears impossible simply awaits the development of more advanced instruments and more meticulous analysis to unveil its true essence. Now, turning to what we might call Part 5 of our investigation. Sounding the alarm. But let's be clear. This alarm isn't a frantic cry warning of imminent catastrophe. Instead, it's a calm, measured signal of scientific curiosity, a cautious alert that something anomalous is unfolding. Think of it as a cosmic smoke detector designed to alert us to potential hazards without triggering unnecessary panic. More of a warning system tuned to subtle signals rather than a blaring siren of imminent danger. The year 2025 is poised to deliver a celestial spectacle that could turn casual stargazers into avid comet hunters. We're about to watch multiple luminous objects ignite simultaneously, each telling its own spectacular tale. These celestial visitors will present photographic opportunities that might only occur once in a lifetime, offering dramatic views of objects racing across star fields with almost choreographed precision. Social media platforms will likely be flooded with time-lapse videos capturing these visitors streaking through the cosmos, creating a visual symphony that appears meticulously coordinated. It's crucial to understand, despite the dazzling display. These comets pose no direct threat to Earth. Comets are inherently fragile assemblies of ice, dust, and organic compounds, loosely held together by their weak gravitational bonds. When solar radiation heats their surfaces, they transform from dark, dormant objects into stunning, glowing apparitions, spectacles that captivate our collective imagination. What we witness during these approaches is not a solid, indestructible object, but rather a slow-motion disintegration, shedding material that will never be recovered, a kind of cosmic slow dance with their own fragile existence. Furthermore, even the closest approaches of our 7 newly observed comets remain safely distant in astronomical terms. For example, Pan-STARRS' nearest pass keeps it well beyond the lunar orbit, while Swan and Stereo follow trajectories that do not pose any conceivable risk to Earth or any other major body in our solar system. These are purely flyby events, celestial visits that occur at safe distances with no imminent collision threat. The real source of alarm, however, doesn't stem solely from the physical danger, but rather from our innate pattern recognition abilities, an evolutionary trait designed for survival. Our brains are hardwired to detect patterns, especially multiple unusual events occurring together, prompting us to seek underlying causes rather than dismissing coincidences as mere chance. This instinct served our ancestors well in identifying coordinated threats or natural dangers in their environment. But in the context of cosmic phenomena, this same pattern-seeking tendency can lead us astray. When we see 7 comets arriving within a relatively short time frame, our minds immediately jump to questions like, who sent them? What force could possibly coordinate such precision across the vast emptiness of space? Why are they all arriving now? Why in such a synchronized manner? These questions become even more compelling when we consider the presence of three interstellar objects, our interstellar visitor designated 3I Atlas, that coincidentally appears at a time that seems too convenient for pure coincidence. The narrative begins to seem almost scripted. An alien probe arrives, a swarm of comets follows, and something extraordinary appears to be unfolding right before our eyes. This sequence, alien craft arrives followed by a seemingly orchestrated comet swarm, practically invites speculation about extraterrestrial influence. Social media algorithms tuned to maximize engagement through mystery and intrigue amplify this storyline. They feed our curiosity with narratives that suggest conspiracy or covert coordination, fueling speculation and driving platform metrics. The combination of these elements, anomalous celestial events and the amplifying power of digital narratives, creates a potent mixture that compels us to look more closely, question more deeply, and consider possibilities that challenge our understanding of the universe. Certainly, here is a deeply enriched and elegantly crafted version of the provided text, expanding on ideas, adding vivid details, and ensuring a seamless flow while maintaining clarity and precision. In today's digital age, videos that hint at covert connections between celestial phenomena tend to garner far more attention and views than those offering meticulous explanations rooted in orbital mechanics and the rigorous application of statistical probability. This disparity reflects a broader human tendency, our collective hunger to find meaning amid the vast, often seemingly random expanse of the universe. As stories grow and narratives develop through retelling, the allure of mysterious patterns and hidden links becomes irresistibly compelling, even when the underlying data might suggest no more than coincidence. This is precisely where our fundamental responsibility, our accountability, becomes critically important. Every bold assertion or extraordinary claim must stand up to the most stringent scientific scrutiny. Such claims should be tested rigorously against the well-established principles of physics and the latest observational data. Speculation, while not only permissible but often encouraged as part of scientific discourse, must be clearly labeled and accompanied by a rigorous evidentiary standard. The line between imaginative hypothesis and verified fact is delicate and must be constantly reinforced. Entertainment, excitement, and captivating storytelling are valuable tools for engaging audiences. However, they are no justification for promoting unfounded theories as factual truths. It is vital to continually emphasize the essential distinction between spectacle and causality. Just because a phenomenon appears dramatic or visually spectacular does not mean it is the result of some orchestrated or artificial influence. Similarly, an impressive display does not inherently imply threat or intentional manipulation. The universe itself offers countless examples of natural phenomena that surpass our aesthetic expectations and challenge our understanding, without resorting to exotic or supernatural explanations. For instance, consider how the heightened solar activity anticipated in the year 2025 will dramatically amplify the visual spectacle of our comet parade. During solar maximum, our star becomes a hub of heightened magnetic turbulence, frequently hurling massive coronal mass ejections, colossal bubbles of plasma, and high-velocity particle streams into interplanetary space. These energetic outbursts can profoundly influence the behavior of comet tails. During intense solar storms, ion tails, those shimmering plasma-like extensions streaming away from a comet, may stretch across multiple degrees of the sky, creating spectacular arcs and ribbons visible to both amateur and professional astronomers. Disconnection events, spectacular phenomena in which segments of a comet's tail appear to break apart or detach, can produce the illusion that the comet is shedding pieces on command. Such effects will undoubtedly generate breathtaking photographs and videos, many of which will circulate widely on social media, giving the impression of synchronized or orchestrated behavior among our 7 visitors. In reality, however, each comet responds independently to the shared, turbulent solar environment. The apparent coordination, tailing, brightening, or disconnection arises from their simultaneous exposure to the same solar activity, not from any form of centralized control or external manipulation. It is akin to observing 7 different weather vanes all pointing in the same direction during a fierce windstorm, an impressive display of shared influence rather than evidence of orchestrated design. This timing of solar maximum adds an intriguing layer to our ongoing investigation. Why does this extraordinary year of comet activity coincide precisely with the peak of the solar cycle? Could there be a deeper connection, perhaps between the cyclic nature of solar activity and the rate at which comets from the distant reaches of the solar system begin their inward journeys? Might gravitational or electromagnetic effects associated with this solar maximum subtly influence the timing of comet arrivals? These questions, while delving into speculative territory, are firmly rooted in observable and measurable phenomena. Solar activity follows well-documented cyclical patterns, roughly an 11-year cycle, that are correlated with various space weather effects. Historical data spanning multiple solar cycles suggest that during periods of heightened activity, the likelihood of observing or discovering comets, especially those making their first appearance, may increase. If a consistent pattern exists whereby the solar maximum enhances the probability of comet discoveries or inbound trajectories, then this relationship should be detectable through careful analysis of long-term observational records. As we develop a framework for our investigation, it is essential to remain vigilant against the subconscious tendency, confirmation bias, to interpret ambiguous or coincidental evidence as supporting our preconceived notions. Our goal is to approach the data with objectivity, rigorously testing whether the apparent correlations are genuine or simply the product of random chance. Only through such disciplined scrutiny can we avoid the pitfalls of seeing patterns where none truly exist, ensuring that our conclusions are grounded firmly in scientific fact, rather than in the allure of compelling stories. When encountering unusual tail behavior in comets, the most prudent initial step should be to investigate the influence of solar storm activity, rather than jumping to conclusions about mysterious or exotic coordination mechanisms. Sudden and dramatic outbursts in brightness should prompt us to scrutinize the comet's intrinsic composition and the effects of solar heating, rather than hastily attributing these phenomena to external unknown triggers. Likewise, when orbital anomalies arise, our first course of action must be to verify the accuracy of measurements and to consider well-understood sources of gravitational perturbations before proposing the existence of unfamiliar influences. This methodical discipline does not diminish the sense of wonder or discourage legitimate curiosity. On the contrary, it ensures that our perception of cosmic mystery remains rooted in empirical observations, calibrated to reality rather than wishful thinking. The universe already offers us a rich tapestry of genuine enigmas. There is no need to fabricate additional mysteries. The clustering of these 7 comets, for example, stands as a statistically significant anomaly that warrants serious scientific inquiry. Such an occurrence is sufficiently rare in the vast expanse of space to justify careful exploration of possible underlying causes. If our detailed analysis concludes that nothing more than a coincidental timing, possibly amplified by advancements in survey capabilities, explains the convergence, then that conclusion itself becomes a valuable piece of knowledge, contributing to our understanding of solar system dynamics. However, if our investigations uncover correlations that significantly surpass what statistical randomness would predict, such as shared orbital relationships, synchronized timing patterns, or behavioral anomalies pointing to common influences. Then we face the possibility that we are witnessing phenomena capable of reshaping our fundamental understanding of planetary and small body interactions within the solar system. Adding to the intrigue, the presence of the interstellar object, 3I Atlas, during this unusual year introduces an unpredictable variable, a wild card, that elevates a mere statistical curiosity into a potentially profound mystery. Interstellar visitors arriving roughly once per decade are genuinely significant when their timing aligns with such anomalous clustering, transforming what might be dismissed as coincidence into a question of cosmic importance. We are not asserting that 3I Atlas directly caused or coordinated the swarm of comets. Instead, we recognize that their coincident occurrence warrants thorough investigation rather than casual dismissal. Even if no direct causal link exists, the correlation could hint at indirect connections, illuminating previously hidden aspects of solar system behavior and interstellar interactions. Our responsibility extends beyond simply avoiding false alarms. It involves vigilant scrutiny to ensure we do not overlook genuine signals amid the noise of speculation. History has shown us that many ideas once considered absurd, initially dismissed as fanciful, have later been validated through meticulous research and accumulating evidence. The key challenge is striking the right balance, maintaining a healthy skepticism that guards against unfounded hypotheses while remaining open-minded enough to recognize and evaluate surprising evidence when it appears. To do this effectively, we must uphold rigorous standards for assessing extraordinary claims. Standards that neither dismiss potentially groundbreaking discoveries out of hand, nor accept flimsy assertions without solid backing. As we prepare to analyze our interstellar visitor in detail, it is worth remembering that many of the universe's most profound breakthroughs began with simple questions about puzzling patterns or anomalies. Sometimes the universe appears to be communicating lessons through subtle coincidences, clues that, when properly interpreted, may lead us to entirely new realms of understanding. Often these lessons are disguised as mere chance, waiting for us to uncover their true meaning through careful investigation and disciplined inquiry. The celestial swarm has issued its silent alarm, prompting us to respond with the meticulous instruments of scientific inquiry rather than succumbing to instinctive panic. Whatever truths lie ahead will be uncovered through precise measurement and rigorous analysis, not speculation or unfounded assumptions. Yet, before we delve deeper into the mysteries unfolding before us, it is imperative that we identify our prime suspect, the enigmatic interstellar visitor whose very timing has sparked a cascade of questions and hypotheses. This object, designated as 3I Atlas, stands as the third confirmed interstellar body to traverse our solar system. It is a cosmic drifter that originated around a star far beyond our own, embarking on a solitary hyperbolic journey through our celestial neighborhood. Unlike the other objects we have discussed, comets born and shaped by the gravitational confines of our solar system, this visitor bears no local origin story, no birth certificate within our planetary system. It is, in the most literal sense, genuinely alien. The significance of this distinction cannot be overstated. Every comet in our 7-member swarm was formed within the primordial chaos of the early solar system, crafted from the same ancient building blocks, ices, rocks, and dust, that later coalesced into planets and moons over 4.5 billion years ago. In stark contrast, 3I Atlas carries with it a chemical and physical signature forged in a different stellar nursery, under conditions we can only begin to fathom. Think of it as receiving a message in a bottle, cast not across an ocean but across the vast gulf of interstellar space, traversing countless light years and eons, drifting through the near-perfect vacuum of the cosmos, bombarded by cosmic radiation. gradually accumulating the chemical fingerprints of its epic voyage. This interstellar traveler's journey likely spanned millions of years, during which it was subjected to the harshest conditions of interstellar space. Its chemical makeup and physical characteristics serve as a rare, tangible sample, an interstellar relic, offering a direct glimpse into the environment and processes of another star system, far beyond the familiar context of our own planetary neighborhood. Most crucially for our ongoing investigation, 3I Atlas poses no threat to Earth. Its current trajectory ensures a safe passage past all major planetary bodies following a hyperbolic path that will ultimately sling it back into the depths of interstellar space, never to return. This is a reconnaissance mission, an exploratory flyby, not an invasion. Assuming, of course, that the concepts of missions and invasions are even relevant when considering what might simply be a wandering chunk of ancient ice, a cosmic ambassador from afar. Adding layers of complexity to its story, 3I Atlas has exhibited comet-like behavior despite its remote distance from the sun, where temperatures should be cold enough to keep its volatile ices frozen solid. Yet observational data unmistakably show that this object has developed a visible coma and tail, a hallmark of active comets. Solar heating at such vast distances, however, should be insufficient to trigger the kind of outgassing necessary to produce these features. This premature activity raises intriguing questions. Could its composition include supervolatile materials that vaporize at extremely low temperatures? Or might there be an internal heat source, perhaps residual heat from formation or some other process, that independently drives outgassing detached from solar influence? Both possibilities open tantalizing windows into the conditions of the stellar system where 3I Atlas originated. Its unexpected activity offers a rare, tangible clue, an interstellar signature that could unveil secrets about planetary formation environments far beyond our solar system. The scientific excitement surrounding such an interstellar visitor stems from its unparalleled status as a direct sample, a cosmic courier, delivering information from a world entirely foreign to our own. Every observation we undertake, be it spectroscopic analysis that reveals the chemical makeup of this interstellar visitor, photometric monitoring that tracks its fluctuating brightness, or astrometric measurements that chart its exact path through space, serves as a valuable window into stellar formation processes beyond our sun's influence. These data points collectively help us understand the origins and characteristics of objects formed in distant star systems, offering insights into the broader architecture of our galaxy's planetary nurseries. However, our current inquiry diverges from this conventional pursuit. Our focus is on a more provocative question. Could this interstellar stranger, designated as 3I Atlas, somehow be linked to the peculiar timing of our 7 observed comets? While such a correlation might simply be a coincidence, a statistical fluke, its potential significance warrants rigorous investigation. The stakes are too high to dismiss casually, especially given the extraordinary implications of uncovering a genuine connection. If a tangible link exists between 3I Atlas and the 7 traditional comets, it should manifest in detectable signatures that withstand scientific scrutiny. These signatures could include timing correlations that surpass what random chance would produce, orbital relationships indicating influences beyond mere coincidence, or behavioral anomalies that suggest a shared underlying force rather than independent paths of evolution. Conversely, if no such signatures are found despite meticulous analysis, then the apparent connection could be dismissed as an intriguing but ultimately meaningless coincidence, an illusion of pattern in the vast randomness of space. Yet the presence of authentic correlations would open a Pandora's box of profound questions about the fundamental forces shaping our cosmic environment. forces operating on scales and through mechanisms that challenge our current understanding of physics. Imagine the startling possibility that an interstellar object, traveling from the depths of space, might influence the behavior of objects within our solar system. Such a capability would imply interaction mechanisms far more subtle and far-reaching than those predicted by contemporary physics, potentially hinting at connections between stellar systems that transcend the conventional gravitational relationships we have long accepted. It would suggest a universe where information or influence can be transmitted across vast interstellar distances in ways we have yet to comprehend, fundamentally altering our view of cosmic connectivity. Even without resorting to exotic or speculative physics, the correlation in timing between 3I Atlas and our comet swarm warrants serious scientific attention. Interstellar objects are exceedingly rare arrivals. Based on current detection rates, they appear perhaps once every decade, and their appearances are expected to be randomly distributed over time, unlinked to any events within our solar system. The likelihood of such an interstellar visitor coinciding with a period of intense comet activity in recent memory appears statistically improbable if events are independent. By a straightforward probability calculation, if interstellar arrivals and comet swarms are truly uncorrelated, their simultaneous occurrence should be a rare event. The more unusual each event individually is, such as the recent surge of comets, the more suspicious their coincidence becomes. Of course, it's vital to emphasize that correlation does not equal causation. A suspicious timing alone does not constitute definitive proof of a connection. Nonetheless, this correlation justifies the detailed, methodical investigation we are undertaking. If the universe is subtly trying to communicate or teach us about hidden relationships between interstellar and local objects, then we must be attentive enough to discern its message. Regarding the visual prospects of 3I Atlas, it is crucial to manage expectations carefully to avoid future disappointment. Unlike some of the more spectacular members of our 7-comet swarm, objects that may brighten to become visible to the naked eye or produce stunning tail displays, this interstellar visitor is likely to remain a faint telescopic object throughout its passage. Its scientific importance, however, far exceeds its visual appeal. Even in its modest appearance, it offers invaluable information about materials formed in distant star systems, the processes of interstellar travel, and possibly the very nature of extraterrestrial objects. For casual observers and amateur astronomers, it may not be a showstopper, but for scientists seeking to unlock the secrets of our galaxy, it is a treasure trove of data waiting to be analyzed. Scientists and astronomers around the world, both professional and amateur, are coming together in a concerted effort to observe and analyze the fleeting passage of interstellar object 3I Atlas. This coordinated campaign aims to maximize the scientific insights we can extract during this rare one-time flyby, an event that, by its very nature, will never recur. Every photon of light captured from this object is an invaluable piece of the cosmic puzzle, offering a direct glimpse into the conditions and materials of a distant stellar system untainted by our solar neighborhood. Because of its hyperbolic trajectory, 3I Atlas is destined for a solitary encounter, a brief visit that will leave no room for second chances or follow-up observations. This campaign also provides our most promising opportunity to investigate whether there might be any subtle connection between 3I Atlas and the 7 comets that are currently entering our solar system. If there are shared anomalies, such as synchronized fluctuations in brightness, tail behaviors that mirror each other, or timing patterns that surpass simple coincidence, they could serve as vital clues. Detecting these would require meticulous, simultaneous monitoring of all 8 objects, enabling us to spot correlations that might otherwise go unnoticed. However, uncovering genuine relationships amid this data presents a significant challenge. Human brains are remarkably adept at pattern recognition. They are wired to find structure and meaning, even where none exists. In noisy, complex data sets, this can lead to the identification of false positives, apparent patterns that are merely artifacts of randomness or cognitive bias. This is especially true when investigators are motivated by the desire to find a connection, which can unconsciously influence interpretation. To guard against such pitfalls, our approach firmly separates objective observation from subjective interpretation. The raw measurements, such as brightness levels, orbital parameters, and spectral signatures, are concrete, measurable facts that reflect reality. When we analyze these numbers to explore potential links, we step into the realm of hypothesis testing, a process that demands scientific skepticism balanced with curiosity. The tools of scientific inquiry, particularly statistical analysis, are essential here. They allow us to quantify the likelihood that observed correlations could have arisen purely by chance, providing a rigorous basis for distinguishing true signals from random noise. Furthermore, independent verification by multiple research teams employing different instruments and analysis methods helps ensure that any pattern we detect is robust and reproducible. Yet, even with the most rigorous statistical scrutiny, human judgment remains crucial. We must carefully evaluate whether the evidence is strong enough to support extraordinary claims, such as the idea that an interstellar visitor is influencing the behavior of native solar system comets. Such a hypothesis, if true, would revolutionize our understanding of how stellar neighborhoods interact across the vast expanses of space. It suggests a universe that might be more interconnected than current theories propose, with subtle yet profound influences operating on scales far beyond human intuition. Alternatively, the observed patterns might simply be statistical flukes, chance coincidences that test our ability to distinguish meaningful relationships from random occurrence. Either scenario warrants thorough investigation. The key to revealing the truth lies in the data itself, in careful objective analysis of the measurements, and in maintaining strict scientific standards throughout the process. Now is the moment to scrutinize our interstellar suspect more closely, understanding that the outcome will shape not only our knowledge of this particular event but also our broader comprehension of the universe's hidden connections. The alien visitor has finally arrived, and its story has been etched into the very fabric of its trajectory, written in the precise geometry of its approach. This is the beginning of a new chapter, one that reveals a path unlike any native object within our solar system. Let's consider this journey as part 7 of our ongoing exploration, the orbit of intrigue. Imagine the path of this interstellar stranger, which resembles a cosmic passport stamped with the signatures of a long voyage through the depths of space. It begins in the vastness beyond our solar neighborhood, tracing a trajectory that both documents a distant origin and hints at an ultimate return to the darkness of interstellar space. Unlike the elliptical orbits that keep planets and traditional comets bound to the sun in a perpetual dance, cycles that repeat endlessly, this object follows a hyperbolic route. Such a trajectory is the mathematical hallmark of an object possessing enough velocity to escape the sun's gravitational pull entirely, never to return. Visualize it as a cosmic slingshot, plunging inward from the far reaches of interstellar space. It dives toward our star with relentless speed, swings around the sun in a sharp, decisive curve, and then accelerates away, back into the void beyond our reach. This is a one-time encounter, no second chances, no loopbacks. What we are witnessing now is a singular passage, a fleeting glimpse of an object passing through our neighborhood in real time. The orbital elements, those precise measurements that define its position and motion, tell a compelling story about where it came from and where it might go next. The trajectory of this interstellar traveler appears to originate from a direction roughly aligned with the constellation Perseus. However, it's essential to remember that interstellar space offers no signposts or markers pointing to specific origins. Stars and cosmic objects are in constant motion, and the path of this visitor is a product of complex initial conditions rather than a clear scenic route. Its hyperbolic excess velocity, the speed it maintains even after escaping the sun's gravitational influence, implies a journey that likely spanned hundreds of thousands of years, originating from the nearest stellar systems capable of launching such an object. What makes this trajectory particularly fascinating and worthy of closer scrutiny is its inclination relative to the ecliptic plane, the flat disk-like region in which the majority of our solar system's planets, asteroids, and comets reside. Most objects within the solar system orbit the sun roughly along this plane, making their paths predictable and well understood. But this interstellar visitor approaches at a modest angle, neither plunging in from high above the plane nor below it, but rather from a somewhat inclined perspective. This near-ecliptic geometry means it passes through a region of space that is not drastically distant from the paths where our 7 comets are now making their inward journeys. This inclination is of particular interest because it influences the likelihood of gravitational interactions with our native solar system objects. An object arriving from a high galactic latitude, coming in from far above or below the plane, would cross through the system with minimal chance of proximity to planets or comets, thus exerting little influence. Conversely, a trajectory that stays within a closer proximity to the ecliptic increases the potential for encounters, though not necessarily close ones. Despite this, the distances involved remain vast, measured in astronomical units, far beyond the reach of direct gravitational influence. The object is still far enough away that it's unlikely to have significantly affected any orbiting body during its passage. Nevertheless, its prolonged journey through the same general region of space, where our 7 comets are actively approaching the sun, raises intriguing questions about potential subtle influences or shared origins. Adding another layer of complexity is the retrograde nature of 3I Atlas's motion. Unlike most solar system objects, where planets and comets orbit the sun in the same direction as the planet's rotation, this interstellar traveler approaches from the opposite direction. This retrograde motion results in relative velocities that surpass those typical of native objects during gravitational encounters. High relative speeds tend to diminish gravitational effects because objects moving swiftly through each other's influence zones spend less time within their mutual gravitational reach. In essence, while this trajectory suggests a prolonged passage through a region where our comets are also traveling, the high velocities involved make close gravitational interactions unlikely. Yet the very nature of this object's approach, the angle, speed, and origin, invites us to reconsider our understanding of how interstellar objects might influence, or at least share space with, our native celestial bodies. Its journey, detailed in the precise mathematics of orbital mechanics, might be brief in cosmic terms, but its implications are profound, urging us to explore every nuance of its passage through the solar neighborhood. If the interstellar object known as 3I Atlas were somehow influencing the orbits of our traditional comets, the fact that it moves in a retrograde manner would actually work against such an interaction by limiting the duration of any potential encounters. Its rapid passage through the solar system reduces the window during which it could exert gravitational effects, making sustained influence less likely. These orbital traits impose critical constraints on our investigation. Any influence that 3I Atlas might have on the swarm of 7 comets would need to operate through mechanisms that do not rely on close approaches or long-lasting gravitational interactions. As we scrutinize the geometric details, the idea of direct shepherding, where an object controls or significantly alters the trajectory of others via close encounters, becomes increasingly improbable. The geometric configuration of the orbit suggests that such close, prolonged interactions are unlikely, especially given the high relative velocities and the brief time frames involved. However, the mere geometric improbability does not entirely rule out all forms of connection. In particular, the timing of key orbital events associated with 3I Atlas, such as its crossings of specific points in its trajectory, could still correlate with unusual behaviors observed in our comet swarm. The significance of orbital nodes, especially the points where 3I Atlas's path intersects the ecliptic plane, becomes especially pertinent here. These nodes are the moments when the interstellar object passes through the general region of the solar system where the comets and their debris trails are concentrated. If some form of interaction or influence exists, these nodal passages represent the most promising opportunities for any external effect to occur. Precise calculations can determine the exact dates when 3I Atlas crosses its ascending and descending nodes, moments that can be predicted with high accuracy using astronomical data. Should these dates align with observed anomalies, such as sudden increases in brightness, tail distortions, or minor orbital shifts, in our 7 comets, such a correlation would strongly suggest a connection that transcends simple gravitational explanations. The core challenge lies in establishing what qualifies as unusual activity within the natural variability of comet behavior. Comets are known for their considerable fluctuations, brightness surges, tail development, and slight orbital changes that can occur as a result of solar heating and outgassing. Because such variations are routine, the standards for evidence must be set high enough to distinguish genuine anomalies from normal cometary responses. To address this, rigorous statistical analysis becomes essential. By continuously monitoring each of the 7 comets and meticulously cataloging all significant brightness changes, tail events, or other noteworthy behaviors, we can compile a comprehensive data set. This data set then allows us to test whether these anomalies tend to cluster around 3I Atlas's orbital milestones more often than pure chance would suggest. The null hypothesis in this context posits that there is no relationship. The observed comet behaviors are randomly distributed over time, independent of the interstellar object's orbital positions or passages. If, upon analysis, we find a statistically significant overrepresentation of anomalies coinciding with these orbital milestones, it would provide compelling objective evidence of some form of connection, though the exact mechanism might still remain elusive. However, we must remain vigilant against biases that could distort our conclusions. There is a natural human tendency to focus on patterns that support a hypothesis while overlooking instances where expected correlations do not materialize. A truly rigorous investigation involves tracking all relevant events, both those that support and those that contradict the hypothesis, so that the analysis remains impartial. Only by considering the full context can we confidently determine whether any observed clustering is meaningful or merely a product of random variation. The orbital progression of 3I Atlas presents further valuable opportunities to investigate potential links with our observed comet swarm. As this interstellar visitor nears its perihelion, the closest approach to the Sun, solar radiation should intensify, leading to increased outgassing activity. This process involves the sublimation of volatile materials from the comet's surface, which could, in theory, trigger observable responses in other objects within the swarm if some form of communication, signaling, or coordination mechanism exists beyond our current understanding. Predictions of the brightness profile for 3I Atlas show a gradual, steady increase as it approaches the Sun, a process driven by solar heating. This brightening trend might be interrupted by sudden outbursts, should volatile compounds vaporize rapidly or internal structural stresses cause fragmentation. Such dramatic events would occur at specific predictable times and positions along the comet's orbital path, based on precise orbital modeling. If the 7 comets in the swarm are somehow responsive to the activity of 3I Atlas, their responses, be it increased brightness, tail activity, or other signs, should align temporally with the predicted brightening and outburst events of the interstellar visitor. The closer the timing of these responses is to the predicted activity peaks of 3I Atlas, the stronger the evidence would be for an actual connection rather than mere coincidence. A tight correlation in time would suggest a genuine, perhaps causal relationship, implying some form of communication or influence. However, we must also entertain alternative explanations. It's possible that what appears as coordinated behavior might simply be the result of all objects reacting independently to common external influences, rather than engaging in direct interaction. Space weather phenomena, such as solar activity, variations in the interplanetary magnetic field, or energetic particle streams, can simultaneously impact multiple objects in the solar system. These effects could produce apparent synchronization in their activity patterns, creating the illusion of coordination without necessitating any direct communication. Such a solar influence hypothesis predicts that any correlated behaviors should be traceable to specific space weather events, solar flares, coronal mass ejections, or high-velocity solar wind streams that interact with the cometary atmospheres in measurable ways. If these triggers are identified, it would favor explanations rooted in well-understood astrophysical processes rather than exotic coordination mechanisms. The orbital features of 3I Atlas further impose constraints on the duration and scope of any potential influence on solar system objects. Its hyperbolic trajectory ensures a swift passage through our neighborhood, taking perhaps only about 18 months from initial detection until it recedes back into interstellar space beyond our reach. This brief window of interaction means that any effects on the comet swarm must manifest relatively rapidly and be observable with current instrumentation. Slow-acting influences, which might accumulate over decades or even centuries, would not have enough time to produce detectable changes during this fleeting visit. As we anticipate the perihelion passage, it's essential to remember that orbital mechanics operate with remarkable precision, governed by gravitational laws that are indifferent to speculative notions of alien coordination or secret signals. The numbers, orbital parameters, timing, and trajectories are objective, unambiguous data points. They tell their own story, one that is rooted in the fundamental physics of celestial motion. Whether this story hints at any connection to the comet swarm remains an open question, and perihelion could be the moment at which this mystery becomes clearer. In essence, what occurs during perihelion will serve as a critical test. The behavior of 3I Atlas, dictated solely by gravitational influences and solar heating, is expected to follow predictable patterns. Any deviations or signals that correspond with activity in the comet swarm, such as sudden brightness increases, tail anomalies, or fragmentation events, must be carefully scrutinized. If timing correlations are observed that surpass what chance would predict, they could hint at something more intriguing. Conversely, the absence of such correlations would reinforce the likelihood that all observed phenomena are simply the result of natural, well-understood astrophysical processes. In conclusion, the perihelion passage of 3I Atlas offers a unique, scientifically rigorous opportunity to evaluate potential connections with our solar system's comet swarm. The well-understood laws of orbital mechanics and solar physics serve as the guiding framework for this investigation. Whether the story told by these celestial objects turns out to be one of natural coincidence or hints at deeper unknown influences remains to be seen. But what is certain is that the precise, predictable nature of celestial motion ensures that the upcoming perihelion will deliver critical data. data that could finally clarify whether there is a hidden link or simply a remarkable cosmic coincidence in this extraordinary year. Perihelion marks the defining moment for any comet, a pivotal point when it reaches its closest proximity to the Sun, transforming a slow, gradual approach into a rapid burst of activity. For the interstellar traveler known as 3I Atlas, this event holds extraordinary significance. It is at perihelion that the comet confronts the full force of our star's radiation and energetic particles, experiencing phenomena unlike those encountered in its distant, cold journey through interstellar space. The physics at play during this close encounter are both well understood and strikingly dramatic. As 3I Atlas advances toward the Sun, the intensity of solar radiation increases dramatically, following the inverse square law. This fundamental principle states that the brightness and heating power of sunlight double with each halving of distance, meaning that even small reductions in distance lead to exponential increases in energy received. The comet's icy nucleus, which during its interstellar voyage remained frozen and largely inactive, begins to respond to this surge in heat. The frozen volatiles, primarily water ice but potentially also more exotic compounds, start to vaporize, forming a gaseous and dusty cloud around the nucleus. This activity transforms what was once a dark, inert object into a luminous, active comet with a glowing coma and a streaming tail, vividly visible against the backdrop of space. However, the chemical makeup of interstellar ice is likely quite different from that of the typical solar system comet. While solar system comets generally contain water ice along with simple organic molecules, 3I Atlas originated in a different stellar environment, formed in the outer reaches of another star's planetary system. Conditions there, such as temperature, pressure, and chemical availability, might have favored the incorporation of molecules like carbon monoxide, carbon dioxide, methane, or even more complex exotic compounds. These differences are crucial because they influence the spectral signatures we can observe during perihelion. Spectroscopy, the analysis of light emitted or absorbed by the comet, serves as our primary tool for uncovering the comet's chemical composition. When the comet's ices vaporize under solar heating, the molecules are excited by the sun's radiation, emitting characteristic spectral lines. Each molecular species produces a unique set of emission lines, acting as a chemical fingerprint that reveals its presence. By studying these spectral features, scientists can reconstruct the comet's original makeup and, by extension, gain insights into the environment in the stellar system where it formed. This spectral fingerprint remains largely unaltered during the million-year journey through interstellar space, offering a window into the chemical conditions of another star's birth cloud. If our investigation uncovers meaningful connections between 3I Atlas and the 7 comets passing through our solar system, perihelion becomes the prime opportunity for revealing these links. The intense solar heating at this close approach might not only maximize the comet's activity, but could also serve as a catalyst, triggering mechanisms that might have influenced the synchronized appearance or behavior of multiple objects. Such mechanisms could involve the sublimation of volatile materials or even subtle interactions among comets, leading to observable phenomena that are both subtle and spectacular. Among the signs to watch for are sudden increases in brightness known as outbursts. These often occur when particularly volatile compounds vaporize rapidly or when fresh, previously shielded ice surfaces are exposed as dust crusts are eroded away. Such outbursts can cause a comet's brightness to increase tenfold or more within just a few hours, creating dramatic visual spectacles and offering vital clues about the internal structure and composition of the nucleus. The development of jets, narrow streams of gas and dust erupting from specific regions on the comet's surface, could produce asymmetrical thrust effects, subtly altering its trajectory. While such non-gravitational forces are well documented in native solar system comets, their presence in an interstellar object like 3I Atlas would be unprecedented, providing unique insights into how materials from other stellar systems respond to our Sun's influence. Of particular interest is the formation and evolution of 3I Atlas's tail system. The tail provides a dynamic, real-time visualization of the interaction between interstellar material and the solar wind, a stream of charged particles emitted by the Sun. As the comet's gases are excited and blown away, they trace out tails that reveal the physical and chemical interactions occurring at the interface between the comet and our star's energetic environment. Observing the tail's shape, length, and response to solar activity will shed light on the nature of interstellar materials, whether they behave similarly to native solar system comets or exhibit distinctive features indicative of their different origins. Such detailed analysis during perihelion will deepen our understanding of how extraterrestrial objects respond to the complex forces at play in our solar neighborhood. Ion tails develop when the intense ultraviolet radiation from the Sun interacts with the gases emitted by a comet, stripping electrons from their atoms and molecules. This process results in the formation of charged particles that are swept away from the comet and stream outward, aligned along the lines of the solar magnetic field. The specific behavior of this ion tail, its length, orientation, and how it reacts to fluctuations in the solar wind, can serve as a revealing indicator of how gases originating from a different stellar system might interact with our Sun's particle environment. Should the ion tail of interstellar objects like 3 Atlas display characteristics that deviate from what is typical in native comets, such as unusual length, shape, or response to space weather, these anomalies might suggest a different chemical or physical composition, thus hinting at materials that are distinct from those formed within our own solar neighborhood. Dust tails, on the other hand, follow physics governed by radiation pressure rather than magnetic influences. The size distribution and makeup of dust particles determine how significantly solar radiation can alter their paths from simple ballistic trajectories. Larger particles, owing to their mass, tend to follow paths very close to the original orbit, barely deviating as they are pushed by sunlight. Conversely, microscopic grains being extremely light can be dramatically affected by radiation pressure, resulting in broad, sweeping, often curved tails that stretch across large sections of the sky. If observations of 3 Atlas reveal an unusually spectacular dust tail, one that appears brighter, more extended, or more intricate than those of typical solar system comets, it could indicate that its composition is unusually rich in fine, responsive particles. Alternatively, an abrupt increase in dust during perihelion, perhaps due to fragmentation, might suddenly expose a reservoir of previously hidden interior material. Such fragmentation events are among the most dramatic phenomena a comet can experience during its close approach to the Sun. As the comet absorbs solar heat, rotational stresses, and internal pressures from vaporizing volatile substances, its fragile structure may fail, causing it to break apart into multiple fragments that drift along the original orbital path. For an interstellar object like 3 Atlas, such a breakup would be particularly significant because it would grant access to pristine interior materials, unchanged since the comet's formation in a distant stellar system. These exposed surfaces could provide a unique, direct sample of matter formed outside our solar system, offering extraordinary opportunities for spectroscopic analysis. A detailed examination of the composition of these fragments could yield insights into the chemical environment of other star systems and the processes that shape cometary bodies in interstellar space. However, fragmentation also introduces complexities into the investigation. Multiple fragments, each following slightly different trajectories, might create an illusion of coordinated activity or unusual behavior that, in reality, is simply the result of the breakup process. The geometric and orbital tracking of these fragments becomes more complicated, and what appears to be a synchronized response might merely be a consequence of their shared origin. Adding to this complexity are the space weather conditions during perihelion, especially under solar maximum scenarios. During such periods, the density of energetic particles in space increases significantly, and the sun's magnetic field becomes more turbulent, with more frequent and intense coronal mass ejections. These phenomena dramatically influence the appearance and behavior of comet tails. They can induce spectacular and sudden changes, tail disconnections, plasma instabilities, and magnetic reconnection events that may cause tails to twist, kink, or even break apart entirely. While each comet responds independently to the immediate environment around it, they are all subject to the same solar triggers, which can produce seemingly synchronized tail phenomena, giving the impression of coordinated behavior where none actually exists. In essence, the behaviors of ion and dust tails during the perihelion passage of interstellar objects like 3 Atlas are highly sensitive to the dynamic conditions of space weather. These effects, tail disconnections, plasma disturbances, and magnetic interactions, are natural responses to the sun's activity, and their occurrence across multiple comets can create illusions of orchestrated activity. Understanding these phenomena requires careful analysis, distinguishing between genuine physical interactions and the shared response to the sun's volatile environment. The fundamental challenge in discerning true external coordination from a mere collective response to solar influences hinges on meticulous timing, precise measurement, and detailed geometric analysis. Disturbances in the solar wind, charged particles streaming outward from the sun, travel across space at velocities that are well understood and predictable. These particles reach different regions within our solar system at calculable moments, allowing astronomers to anticipate their effects on comets with remarkable accuracy. If the unusual behaviors observed in our 7-member comet swarm, such as sudden brightening, tail formation, or minor orbital shifts, correlate with events involving the interstellar object known as 3I Atlas, but cannot be convincingly explained by the expected delays associated with solar wind propagation, then that correlation takes on extraordinary significance. It suggests that something beyond random coincidence might be influencing the comets in a manner that warrants serious investigation. Across the globe, amateur astronomers are actively preparing coordinated observation campaigns to monitor 3I Atlas as it approaches perihelion, the closest point to the sun in its trajectory. This distributed network of citizen scientists provides a level of coverage that no single observatory could achieve alone. Equipped with telescopes, cameras, and tracking tools, these dedicated observers will generate continuous light curves, detailed records of brightness variations over time, and photographic documentation capturing the development of tails, fragmentation events, or other signs of activity. They will also issue real-time alerts should any dramatic outbursts or sudden changes occur, allowing for rapid follow-up observations. This grassroots effort complements the work of professional facilities with space-based telescopes, ground-based observatories, and specialized comet surveys, all contributing to what will be the most comprehensive scientific investigation of an interstellar visitor to date. Every photon of light captured during this period is invaluable. It constitutes irreplaceable data that can reveal conditions in another stellar system, offering insights into the composition, behavior, and physical processes of materials originating from beyond our solar neighborhood. Simultaneously, our study demands parallel monitoring of all 7 traditional comets, each with distinct origins and trajectories, during the same observational window. By comparing their behaviors, scientists aim to identify anomalies, subtle deviations in brightness, tail morphology, or orbital parameters that might be correlated with the events involving 3I Atlas. This comparative approach is essential in distinguishing between natural variability, common in cometary activity, and anomalies that could suggest a more profound, perhaps exotic, influence. The level of precision required in this endeavor pushes current observational technologies and methodologies to their utmost limits. Detecting faint signals, such as slight brightness fluctuations, minor asymmetries in tail structure, or subtle shifts in orbital inclination, is a formidable task, often requiring the most sensitive instruments and meticulous data analysis. These small variations, however, could be the only clues indicating interactions operating beneath the threshold of conventional detection methods. As we approach perihelion, it's vital to remember that the universe adheres steadfastly to the laws of physics, laws that remain constant regardless of human expectations or hopes for groundbreaking discoveries. 3I Atlas will likely respond to the intense solar heating by brightening, developing tails, and potentially fragmenting. Behaviors driven solely by its intrinsic properties and the natural physics of solar heating. These processes are not orchestrated to produce spectacular displays for human observation, but are fundamental responses rooted in the object's composition and structure. Within these natural phenomena lie the potential for profound scientific breakthroughs. The way interstellar materials behave when exposed to our sun's environment could reveal new insights into their origins, chemical makeup, and physical properties. Whether these observations establish a direct connection to our seven-comet swarm or remain separate phenomena is an open question, one that can only be answered through diligent, careful observation. The universe's clockwork mechanisms, governed by immutable physical laws, continue their precise operations, indifferent to human speculation or desire for extraordinary revelations. They provide the steady stream of data necessary to differentiate between baseless conjecture and genuine scientific discovery, ensuring that our interpretations are rooted in objective evidence. Part 9 focuses on the relationship between the comet swarm and the Sun. Our star operates on cycles far exceeding human attention spans, shifting between tranquil periods and phases of intense activity with the regularity of a cosmic metronome. As 2025 approaches its solar maximum, the peak of the 11-year solar cycle, our Sun becomes notably more active, unleashing increased solar flares, coronal mass ejections, and energetic particle streams. These phenomena not only shape space weather but also influence the observable behavior of comets passing through the inner solar system. During solar maximum, the heightened activity can dramatically enhance comet tail phenomena. Magnetic fields and energetic particles interact with cometary gases, causing tails to twist, kink, or even disconnect, a process known as tail disconnection events. These dramatic visual effects are not only spectacular to observe and photograph, but also serve as natural laboratories for studying solar-terrestrial interactions. Understanding these processes is crucial because they highlight how the same solar phenomena that produce dazzling auroras and disrupt satellite communications can also influence comet behavior. The intensified solar wind and magnetic disturbances during this period can temporarily alter the approximately 11-year cycle of solar activity, which dictates many of the Sun's energetic behaviors, is reaching its peak in the year 2025. As a result, our star is transforming into a far more volatile and visually spectacular version of its usual self. During this solar maximum, the Sun produces an extraordinary abundance of sunspots, those ominous dark patches that mark regions where intense magnetic fields puncture the star's surface. These magnetic concentrations are capable of storing vast amounts of energy, which on occasion are suddenly released in explosive outbursts. Such releases propel torrents of charged particles and electromagnetic radiation outward into space, traveling at speeds that can cross the vast expanse of the solar system in just a matter of hours or days. This heightened solar activity has a profound impact on our ongoing investigation of 7 comets, as well as the broader environment in which they travel. The increase in energetic particles and the strengthening of magnetic fields during solar maximum can significantly amplify the observable behaviors of comet tails, making even modest objects appear far more dramatic and luminous than they would during periods of relative solar calm. For example, consider a coronal mass ejection, a colossal bubble, sometimes weighing 1 billion tons, of magnetized plasma hurled away from the sun's corona. When such a powerful burst interacts with a comet's fragile ion tail, it can induce dramatic and rapid changes. The shock waves and magnetic field distortions caused by these ejections can lead to the compression, twisting, or even complete severance of a comet's tail. These events unfold swiftly, often within a few hours, and can produce some of the most striking and photographic spectacular images of comets ever captured. Such tail disconnection events occur when the magnetic fields carried by the solar wind undergo rapid polarity shifts, changes that the comet's existing tail structure cannot accommodate or resist. In these moments, the comet's old tail is effectively shed and drifts away as space debris, while a new tail begins to form in the altered magnetic environment. To the untrained eye, these phenomena can seem almost supernatural. A comet's tail might suddenly develop kinks, knots, or spiral shapes that seem to defy the simple physics of gas streaming smoothly away from the nucleus. Sometimes the tail appears to break off entirely, creating an illusion that some external force, an unseen attacker or destructive influence, has damaged or attacked the comet. In reality, these are perfectly normal responses to the extreme and fluctuating solar conditions characteristic of solar maximum. The comet itself remains unaffected. Only its glowing ionized gas tail reacts to the dynamic magnetic environment. The visual spectacle of these tail phenomena can be so intense and unusual that observers often search for exotic or alternative explanations, rather than attributing the changes to well-understood space weather processes. This tendency is particularly relevant to our current investigation, which involves 8 objects in total: 7 traditional comets and the interstellar visitor, 3I Atlas. All of these objects are subjected to the same space weather environment. They experience the same coronal mass ejections, the same high-velocity streams of charged particles, and the same magnetic field variations that define solar maximum conditions. If multiple comets exhibit sudden and synchronized tail disconnection events during this period, the most straightforward and scientifically grounded explanation is that they are responding collectively to shared solar triggers. Such simultaneous behavior does not necessarily imply any mysterious or coordinated action among the objects themselves. Instead, it reflects their common exposure to the intense, turbulent environment created by the sun's heightened activity. This shared response to solar phenomena is a well-understood aspect of space weather, and it underscores how natural, largely predictable processes can produce spectacular and seemingly synchronized effects across multiple celestial objects. A powerful solar storm has the capacity to influence the appearance and behavior of comet tails across the entire inner solar system, often producing a false impression of synchronization among these celestial visitors. This phenomenon occurs because a single large-scale solar event can trigger widespread effects in the space environment, leading to coordinated tail activity that is purely coincidental, rather than the result of any communication or direct interaction between the comets themselves. The heightened solar activity predicted for the year 2025 further amplifies this effect by impacting Earth's magnetosphere in ways that heighten the drama of the year's astronomical display. During periods of intense solar storms, energetic particles emitted by the sun can cause geomagnetic disturbances on Earth, disrupting satellite communications, interfering with global positioning systems, and in extreme cases risking damage to electrical power grids. These storms also have a more visible and dramatic consequence. They push the aurora borealis and aurora australis, those mesmerizing dancing lights, toward lower latitudes, allowing observers situated in moderate geographic locations to witness phenomena typically confined to polar regions. When combined with the active comets streaking across the sky, this creates a spectacle of such intensity and synchrony that it can seem almost otherworldly in its timing and appearance. However, it is vital to distinguish between cause and mere correlation in these relationships. While solar storms influence both comet tails and Earth's magnetosphere simultaneously, the comets themselves do not cause geomagnetic disturbances. Instead, both phenomena are driven independently by the same underlying cause: the Sun's fluctuating magnetic activity and energetic particle emissions. These effects happen concurrently, sharing a common timeline without implying any direct causative link between the comets and terrestrial impacts. Recognizing this distinction is crucial, especially when evaluating claims that suggest a connection between the interstellar object 3I Atlas and various Earth-based phenomena. If during the passage of the 7 notable comets or the interstellar visitor, satellite systems experience failures or power grids face disruptions, it is far more scientifically plausible to attribute these issues to solar activity rather than to any exotic influence exerted by a small, distant comet. The timing of the solar maximum, when solar activity reaches its peak, raises compelling questions about possible correlations with the patterns of comet discovery and arrival. Could the enhanced solar activity somehow influence the rate at which comets leave the outer reaches of the solar system and journey sunward? Might electromagnetic or gravitational effects associated with the solar maximum alter the timing of these inward-bound comets? These questions, though speculative, are rooted in observable phenomena. Solar cycles are well documented and leave measurable signatures in the behavior and timing of comets' arrivals. Historical data covering multiple solar cycles can be analyzed to determine whether periods of heightened solar activity tend to correspond with increased comet activity. More comets appearing or arriving earlier than statistically expected by chance alone. To accurately interpret these phenomena, it is essential to carefully separate the effects of the Sun from any potential connections to the unusual cluster of comets and the interstellar object. When anomalies such as unusual tail behavior or outbursts occur, the first step should be to consult space weather monitoring systems for documented solar triggers, such as coronal mass ejections, high-speed solar wind streams, or magnetic storms. Only after these standard and well-understood influences are accounted for can more exotic explanations be legitimately explored. This disciplined approach is vital for preventing premature or unfounded conclusions, which can arise when conventional causes are ignored in favor of sensationalist theories. Recognizing the difference between the effects of known solar activity and speculative causal links ensures that scientific investigations remain grounded in verifiable evidence, maintaining integrity and clarity amid the natural complexity of the solar system's dynamics. Advanced space weather monitoring systems provide us with continuous real-time data about the Sun's activity, enabling us to make precise correlations between solar phenomena and the behavior of comets observed in our skies. Instruments such as the Solar and Heliospheric Observatory, the Solar Dynamics Observatory, and a network of ground-based magnetometers actively track the Sun's conditions, monitoring how energetic solar particles and magnetic fields propagate through interplanetary space. This extensive infrastructure grants us an unprecedented capability to differentiate between comet responses driven by known solar influences and those that might be genuinely anomalous, events that could hint at other, as yet unidentified, forces at work. If our interstellar visitor 3I Atlas somehow exerts an influence on the traditional comets, we would expect to observe signatures of this effect emerging clearly above the natural background variability caused by the sun's fluctuating activity. Amateur astronomers and citizen scientists play a vital role in this endeavor, offering crucial supplementary observations that complement the high-tech systems operated by professional space weather agencies. Across the globe, dedicated comet photographers meticulously document tail structures, brightness fluctuations, and morphological changes, often capturing details at a temporal resolution that surpasses that of even the busiest professional observatories. This widespread distributed network of observers ensures continuous coverage of our entire comet ensemble, generating comprehensive data sets that are perfect for in-depth correlation analyses. The richness of this observational record is key. The more detailed and complete our collective data becomes, the greater our confidence in identifying truly unusual events, those rare occurrences that deviate from expected patterns and warrant closer scientific scrutiny. The active solar environment of the year 2025 promises a landscape densely populated with space weather phenomena. Frequent solar flares, coronal mass ejections, and magnetic disturbances will create a dynamic backdrop against which our comet investigation unfolds. Such an energetic solar environment offers many opportunities for breathtaking comet photography, with tail disconnections, brightening outbursts, and structural evolutions captured in spectacular detail. However, it also complicates efforts to discern subtle influences, effects that might operate independently of or in conjunction with solar triggers. The challenge for researchers is to uphold rigorous standards for evidence, ensuring that only well-substantiated anomalies are flagged for further investigation, while remaining open to discovering genuine, previously unknown aspects of comet behavior. History has shown us that the universe can surprise us with subtle, delicate connections that initially seem impossible to conceive. The heightened activity during solar maximum may provide the energetic conditions necessary to detect weak interaction effects, should they exist. As we prepare to examine the potential impact of space weather on terrestrial conditions, it's important to remember that the sun's behavior is ultimately the primary driver of the most dramatic phenomena associated with active comets. The well-established link between solar activity and cometary responses is undeniable. The question now is whether additional influences, perhaps operating alongside solar effects, could be at play in ways that current scientific models do not yet predict. This cosmic choreography, guided by magnetic fields, charged particle streams, and solar wind, connects our star to every object within its gravitational domain. Within this familiar dance, however, there may be new steps awaiting discovery. Subtle movements that could reveal deeper layers of the interaction between solar and cometary phenomena. Part 10. Echoes on Earth. The influence of space weather extends beyond the celestial, weaving a complex web of vulnerabilities that most people are unaware of until their technological systems suddenly begin to fail. During periods of heightened solar activity, the energetic particles and magnetic disturbances can disrupt satellite communications, impair navigation systems, and even threaten the stability of power grids. These effects are not always immediately apparent but can have widespread and serious consequences for modern society. Understanding and monitoring this space weather is crucial, especially during the active phases of solar cycles like the one predicted for 2025. As the sun unleashes more frequent and intense storms, the risks to our technological infrastructure grow. Yet, despite the potential for disruption, most of us remain oblivious to these vulnerabilities until a critical system fails, highlighting the importance of continued vigilance, research, and preparedness in safeguarding our digital and electrical lifelines. While comets themselves pose no immediate danger to our planet, the heightened solar activity that often accompanies their spectacular tails can have serious repercussions for the delicate electronic infrastructure upon which modern civilization relies so heavily. When the sun unleashes intense bursts of energetic particles during solar storms, the resulting geomagnetic disturbances, termed geomagnetic storms, can induce powerful electrical currents within our power transmission networks. These currents are capable of overloading transformers, causing widespread failures and triggering cascading blackouts that can leave millions in the dark. The infamous storm of March 1989, which abruptly collapsed Quebec's entire electrical grid, vividly demonstrated how space weather phenomena can translate into tangible terrestrial consequences, disrupting daily life and economic activity across vast regions. Satellites orbiting high above the Earth's atmosphere face an even more direct threat. Accelerated high-energy protons and electrons, energized during solar storms, can penetrate spacecraft shielding, sometimes with devastating effects. These particles may cause temporary malfunctions, such as glitching sensors or communication disruptions, or inflict permanent damage on sensitive electronic components. During periods of intense solar activity, critical systems like GPS navigation, satellite communications, and weather monitoring become less reliable, jeopardizing everything from everyday navigation to global data exchange. Aviation adds yet another layer of vulnerability, especially for flights traversing polar regions. Unlike most parts of the Earth where the magnetic field offers substantial protection against cosmic radiation, polar areas are more exposed due to the geometry of Earth's magnetic shield. During severe geomagnetic storms, airlines often reroute flights to avoid these high radiation zones, prioritizing passenger safety and the integrity of onboard electronics. Such operational adjustments are made routinely during space weather events, highlighting how interconnected our technological systems are with the activity of our star. These phenomena also generate a complex psychological environment when it comes to interpreting claims about potential links between celestial events, like comet activity, and disturbances on Earth. When a sudden spike in comet brightness coincides with the peak of solar maximum, the timing can seem suspiciously perfect, fueling notions of exotic influences or direct connections. Power outages, communication breakdowns, and navigation failures during these periods might be perceived as evidence of some hidden force or cosmic conspiracy involving the unusual swarm of comets. However, the reality is far more mundane yet equally compelling in its own right. Solar storms influence both the behavior of comets and Earth's technological systems through entirely separate mechanisms. Comets respond primarily to enhanced particle densities and magnetic field fluctuations in space, changes driven by solar activity, while Earth's infrastructure reacts to the same particle streams when they interact with our planet's magnetosphere. The apparent correlation arises because both effects stem from a common solar origin, not because the comets are directly manipulating terrestrial systems. This crucial distinction becomes especially significant when considering the interstellar visitor known as 3I Atlas. If, during the passage of this object, satellite systems falter or power grids experience disruptions, the more plausible explanation lies in the intense solar activity rather than any direct influence from the small, distant interstellar body. The temptation to attribute these terrestrial disturbances to the timing of comet activity must be resisted, as it often leads to unwarranted speculation. Instead, scientists and responsible agencies rely on well-understood physical mechanisms, like geomagnetic induction and space weather forecasting, to explain these effects. To manage the risks posed by solar storms, government agencies responsible for space weather monitoring have developed sophisticated warning systems. These systems track the emergence of solar flares, monitor the propagation of energetic particles through interplanetary space, and predict their impact on Earth's magnetic shield. By doing so, they provide critical advance notice, allowing power grid operators, satellite controllers, and airlines to take protective measures, such as rerouting flights or powering down vulnerable equipment before the worst effects arrive. This proactive approach underscores the importance of understanding and anticipating space weather, rather than jumping to sensational conclusions about exotic causes. Earth's magnetic shield, known as the magnetosphere, plays a crucial role in protecting our planet from the barrage of charged particles emitted by the sun. To monitor and forecast these space weather phenomena, the National Oceanic and Atmospheric Administration's Space Weather Prediction Center diligently issues alerts and warnings with the same urgency and seriousness that we associate with severe terrestrial weather events. This comprehensive network of sensors and instruments enables scientists to establish precise correlations between documented space weather activity, such as geomagnetic storms, and any technological disruptions that might occur concurrently. When infrastructure failures happen during periods of intense geomagnetic disturbance, the likelihood that solar activity is the root cause becomes significantly higher than the notion that mysterious comet influences are at work. The heightened solar activity expected in the year 2025 guarantees numerous such opportunities for correlation. During solar maximum, the period when the sun is most active, geomagnetic storms can erupt multiple times within a single month, creating a series of chances for coincidental timing between disruptions in our technological systems and observable comet activity. It's important to recognize that some of these apparent correlations will inevitably result from pure chance, without any underlying causal link. Adding an extra layer of vigilance, amateur radio operators serve as a vital distributed monitoring resource. Their widespread real-time observations often detect space weather effects before official systems can issue warnings. During geomagnetic storms, the propagation of radio waves through Earth's ionosphere becomes dramatically altered, leading to communication blackouts and unusual skip patterns, distorted radio signals that experienced operators can immediately recognize. This network of citizen scientists and hobbyists provides continuous supplementary data that enriches our understanding and can help differentiate between genuine solar-driven phenomena and anomalies that might suggest other influences. If hypothetically the interstellar object known as 3I Atlas were to somehow influence Earth's electromagnetic environment, such effects should be possible to detect through the coordinated efforts of multiple independent monitoring systems. The scientific process requires constant vigilance against the human tendency to misattribute causality, especially when multiple dramatic events unfold simultaneously or in quick succession. Our brains are wired to seek explanations for correlations in time, often imagining causal links where none exist, especially when the timing appears purposeful or meaningful. The more extraordinary or rare the individual events are, the more convincing their coincidence may seem. However, statistical analysis shows that clusters of seemingly related events are actually quite common in large, complex systems. For instance, flipping a coin 1,000 times will eventually produce streaks of heads or tails that seem improbable, but are entirely within the realm of probability. The same principle applies to the apparent coincidence of space weather phenomena, comet activity, and technological failures. These can all align purely by chance. The real challenge lies in developing objective, scientifically rigorous criteria for distinguishing between meaningful patterns and those that arise randomly due to natural variability. This involves establishing baseline expectations for how often certain events should coincide purely by statistical chance, and then rigorously testing the observed correlations against these predictions. Fortunately, professional space weather research has pioneered sophisticated analytical tools designed explicitly to address these challenges, helping scientists separate genuine causal relationships from mere statistical noise. Modern analytical techniques such as superposed epoch analysis, cross-correlation functions, and a suite of other statistical tools serve as vital instruments in unraveling the potential relationships between diverse phenomena, be they celestial or terrestrial. These methods are meticulously designed to quantify the strength and significance of correlations, all while carefully accounting for the pervasive problem of multiple comparisons. When scientists test numerous possible links simultaneously, the risk of identifying spurious correlations, false positives, rises markedly. These advanced frameworks help maintain scientific rigor by distinguishing genuine signals from mere chance, ensuring that claims of connection between interstellar events, such as the passage of 3I Atlas, and Earth-based disturbances are evaluated with appropriate skepticism and precision. The standards for evidence in this domain must be set high enough to prevent premature or erroneous conclusions, false alarms that might cause unnecessary concern, yet remain sufficiently sensitive to detect authentic signals if they indeed exist. In our interconnected age, the extensive reach of modern technological infrastructure introduces both an abundance of opportunities and a set of challenges. With millions of satellites orbiting Earth, billions of electronic devices functioning continuously, and countless communication systems transmitting data across the globe, failures and disruptions happen every day. Many of these incidents are simply the result of natural variability, random technical faults, or aging components. However, during episodes of heightened comet activity or unusual solar phenomena, these routine failures can be magnified in importance. What might typically be dismissed as normal wear and tear, such as a power outage attributed to equipment aging, might, under the scrutiny of heightened astronomical interest, be misattributed to exotic influences from celestial events. This tendency underscores the importance of education and transparent communication. By fostering a clear understanding of how space weather, solar flares, geomagnetic storms, and other phenomena genuinely impacts terrestrial systems, we reduce the likelihood of misinterpretation and unwarranted fears. When the public and scientific community alike comprehend the well-understood mechanisms through which solar activity influences satellites, power grids, and communication networks, the impulse to ascribe unexplained disruptions to mysterious cosmic influences diminishes. This approach extends to our ongoing investigation into potential links between the passage of 3I Atlas and the unprecedented swarm of comets observed in 2025. Maintaining a strict boundary between established cause and effect relationships and speculative or unfounded hypotheses is paramount. Such discipline enables us to explore unconventional ideas, like the possibility of exotic influences, without inadvertently promoting them as established facts. It's essential to ensure that the quest for understanding does not compromise scientific integrity by blurring the line between evidence-based science and conjecture. The increasingly sophisticated technological landscape of modern civilization provides both an advantage and a complication. Our heightened sensitivity to electromagnetic phenomena and space weather effects allows us to detect subtle signals that might have gone unnoticed in the past. These capabilities have the potential to reveal faint influences, perhaps hinting at mechanisms operating below the threshold of conventional effects. However, this very sensitivity also creates more avenues for false correlations, where coincidental timing or measurement noise might be mistaken for meaningful causation. As we prepare to interpret the data, it's crucial to remain aware of the influence of human psychology and cultural narratives. Our minds are naturally inclined to seek patterns and assign significance, even where none exists, especially in times of uncertainty or extraordinary events. Recognizing this cognitive bias helps us approach the data with balanced skepticism, ensuring that our conclusions are rooted firmly in physical reality rather than wishful thinking or anecdotal associations. It's important to reaffirm that Earth's response to space weather follows well-understood and predictable mechanisms. The effects of solar storms, geomagnetic fluctuations, and electromagnetic disturbances are governed by physical laws that have been thoroughly studied and modeled. Even during periods of intense comet activity, the impacts on our technological systems, such as satellites, power grids, and communication networks, manifest in ways that are consistent with established science. These effects can be measured, analyzed, and attributed to the actual sources like solar flares or geomagnetic storms, without resorting to exotic explanations. In essence, the universe's physics remain constant regardless of human expectations or fears. The apparent correlations between celestial phenomena and terrestrial disruptions are often the result of shared underlying causes, primarily solar activity, that influence both the space environment and our technological infrastructure. Recognizing this is fundamental to maintaining scientific integrity and avoiding misattributions that could distract from understanding genuine physical processes. Yet hidden within the vast background of normal space weather fluctuations, subtle signals may still be lying in wait, detectable only by instruments refined enough to differentiate genuine correlation from mere coincidence. Our ongoing inquiry remains firmly rooted in the principles of established physics, while simultaneously remaining vigilant for phenomena that could potentially challenge or expand our current understanding of how celestial and terrestrial forces interact across incomprehensibly large scales of space and time. Part 11. Harbingers of Change. Throughout the course of human history, bright comets have often been perceived as cosmic messengers, portents that cultures around the world have interpreted through the lens of their deepest fears and highest hopes. These celestial visitors, appearing unexpectedly in the night sky, have historically sparked a wide range of interpretations, transforming objective astronomical phenomena into powerful symbols of fate, inevitable change, and cosmic significance. The arrival of multiple comets simultaneously in particular resonates deeply with psychological patterns that have influenced human behavior for millennia. Such clustered appearances tend to elevate objective events into subjective narratives, compelling societies to seek meaning in the seemingly synchronized arrival of these icy visitors. Take, for example, the meticulous records of ancient Chinese astronomers who paid close attention to comet appearances, often correlating these events with significant societal shifts. They described comets as broom stars, metaphors pointing to their sweeping motion across the sky, and linked their appearances to dynastic changes, natural disasters, and social upheavals. These records reveal that civilizations have long sought to find significance in the timing and patterns of celestial phenomena, often interpreting them as signs of divine or cosmic approval or disapproval. In medieval Europe, chroniclers also assigned profound importance to comets, frequently viewing them as divine warnings of impending calamities or epochal transformations. The Great Comet of 1166, which appeared shortly before the Norman conquest of England, became inseparably linked with the fall of Saxon rule and the reshaping of the English social order. Whether the comet directly influenced those historical events remains a matter of debate, but the symbolic association endured, embedding itself deeply into collective memory. Similarly, the return of Halley's Comet in 1758 coincided with the 7 Years' War, a conflict that redrew political boundaries across 3 continents. Different cultures perceived this celestial event through contrasting lenses. Colonial Americans saw it as an omen heralding independence from Britain, while European scientists celebrated it as a validation of Newton's gravitational theories. These seemingly contradictory narratives underscore how the same cosmic event can be woven into diverse cultural and political stories, depending entirely on context and perspective. These historical examples illustrate a fundamental aspect of human cognition. We naturally tend to connect clusters of unusual events into coherent stories that seem to carry deeper meaning, stories that often feel more significant than the randomness of coincidence. When multiple dramatic phenomena occur simultaneously, be they comets, wars, plagues, or social upheavals, our instinct is to seek underlying connections rather than accept them as independent, unrelated occurrences. This pattern-seeking behavior becomes especially pronounced during times of societal stress or widespread uncertainty. In such periods, populations are actively searching for signs or messages that might point to future directions, impending change, or divine will. The 2025 swarm of comets arrives amidst a world marked by rapid technological advancement, escalating climate concerns and geopolitical tensions, an environment ripe for interpreting celestial events as harbingers of transformation. In today's digital age, this ancient psychological tendency is amplified through modern media ecosystems, an ecosystem that would astonish even the most imaginative medieval chronicler. Algorithms designed to maximize engagement often promote sensational narratives, turning celestial phenomena into stories of cosmic portent and impending upheaval. The mechanisms that drive social media amplification serve to magnify these patterns, making the interpretation of comet clusters into meaningful symbols not just a cultural tendency, but a widespread phenomenon reinforced by the very architecture of information dissemination. Social media algorithms are inherently designed to prioritize content that captures attention and evokes emotional engagement, often at the expense of presenting accurate or nuanced information. This means that dramatic videos of comets streaking across the sky and speculative theories about extraterrestrial influence tend to spread more rapidly and widely than carefully crafted, scientifically grounded explanations. The neural pathways that originally helped humans identify genuine patterns in their natural environment, such as signs of danger, food sources, or seasonal changes, have become highly responsive to the stimuli of the digital age. These stimuli are meticulously engineered to attract, hold, and maximize viewer engagement, leveraging our innate tendency to seek out compelling stories. Amateur content creators equipped with advanced video editing software and accessible tools can produce visually impressive narratives that blend authentic comet imagery with evocative music, dramatic narration, and carefully curated visual effects. These productions can rival professional quality documentaries, yet they often promote ideas that would struggle to withstand scrutiny in peer-reviewed scientific journals. The democratization of content creation means that anyone with internet access can contribute to the evolving narrative surrounding celestial events, fueling a flood of interpretations, many of which are shared spontaneously and independently by multiple creators. Without deliberate coordination, these creators often arrive at similar conclusions or themes, creating a false impression of widespread consensus or collective belief about the significance of the phenomena. This decentralized storytelling process can accelerate the transformation of straightforward astronomical observations, such as the arrival of 7 comets in the year 2025, into elaborate, emotionally charged narratives. These stories may frame the event as a sign of cosmic importance, suggest alien visitation, or predict apocalyptic consequences. Each retelling introduces new layers of detail, hypothesized connections, and interpretations that diverge progressively from verifiable scientific facts, drifting into realms of pure speculation and myth-making. In this fertile environment of creative interpretation, the presence of an interstellar visitor like 3I Atlas during a year already rich with unusual comet activity provides an especially potent catalyst for storytelling. The human mind naturally seeks to find purpose or intent behind coincidental timing, and the arrival of an extraterrestrial object at precisely the same time as a flurry of comet activity offers an intriguing, almost irresistible narrative hook. The story practically writes itself. An alien probe, deliberately or unintentionally coordinating with comets to deliver messages or warnings to Earth. Such ideas satisfy multiple psychological needs. They explain the seemingly strange timing, assign agency to seemingly random celestial events, and elevate human observers to the role of witnesses to a cosmic drama of profound significance. Professional astronomers, however, face mounting challenges in competing with these emotionally compelling stories for public attention and understanding. Despite their expertise in explaining orbital mechanics and the statistical likelihood of certain celestial configurations, their careful, cautious narratives often lack the immediate emotional resonance of stories that cast observers as active participants in a grand cosmic narrative. Scientific uncertainty, when presented as ranges of possibilities rather than definitive statements, can seem less convincing than confident assertions of hidden motives or deliberate interference. Consequently, maintaining factual accuracy in this environment demands constant vigilance. It requires resisting the temptation to overstate the significance of correlations that, while exceeding what might be expected by chance, do not necessarily prove causation. Emphasizing that correlation does not imply causation is essential, but doing so risks losing the audience's engagement to sources that promote more sensational explanations. Balancing honesty about uncertainties with the need to communicate effectively and responsibly remains a persistent challenge for scientists and communicators alike. This challenge, however, also opens a unique avenue for science education, one that surpasses the reach of conventional astronomy outreach. The widespread public fascination with our study of the 7 comets creates invaluable opportunities to teach core scientific principles. Hypothesis testing, statistical analysis, and the critical difference between evidence and interpretation. By deliberately maintaining a clear boundary between established facts and speculative notions, we serve as models for the scientific method itself, demonstrating how inquiry advances through transparency and rigor while still daring to explore ideas that challenge accepted boundaries. This process becomes more than just a lesson in data. It transforms into an exercise in critical thinking. It shows vividly that truly extraordinary claims demand extraordinary evidence, yet it also underscores the importance of remaining open-minded to unusual observations, even if they appear improbable at first glance. People's interpretations are inevitably colored by their cultural and psychological perspectives, which shape their conclusions regardless of the evidence presented. Those eager to find signs of alien visitation may interpret ambiguous results as supporting their favorite theories, while skeptics rooted in conventional science might dismiss even compelling correlations as insufficient proof of exotic influences. Such polarization reflects deeper philosophical questions about epistemology, the study of how we define reliable knowledge and determine what counts as enough evidence to accept a claim. Different communities shaped by their unique experiences, educational backgrounds, and philosophical outlooks apply varying standards for what constitutes credible proof. The scientific approach, however, advocates provisional acceptance. Conclusions are accepted based on the best available evidence but remain open to revision as new data emerges. This stance of intellectual humility might seem weaker compared to the unwavering certainty of true believers or the rigid skepticism of staunch skeptics. But paradoxically, it is this very flexibility that grants science its greatest strength. It allows us to distinguish genuine discoveries from mere wishful thinking. Throughout history, astronomy has been replete with examples of ideas once deemed absurd that later proved correct after evidence accumulated, as well as theories that, despite initial promise, failed under the scrutiny of more precise observations. Our current investigation into potential links between the interstellar object 3I Atlas and our unusual comet swarm must navigate these cultural and psychological currents carefully, without being swept away by them. The evidence itself, when rigorously analyzed, will ultimately speak, but only if we uphold strict standards of interpretation, remaining sensitive to signals that could challenge conventional assumptions. As we prepare to delve into some of the most sensational and speculative aspects circulating in public discourse about our comet research, it's vital to remember that human curiosity about cosmic mysteries is rooted in a profound desire to understand our place in the universe. This wonder is legitimate and valuable. It fuels exploration and inspires discovery. The real challenge is channeling that innate fascination into questions that can be addressed through meticulous observation and analysis. The ancient skywatchers, those early patterers seeking omens in comet tales, weren't entirely mistaken. They recognized that these celestial phenomena held meaning, even if their interpretations were rooted in symbolism rather than science. Today, with the tools of modern astronomy, we aim to transform that wonder into a rigorous pursuit of knowledge, guided by evidence and critical inquiry. Celestial phenomena serve as invaluable clues, revealing the intricate cosmic processes that influence human civilization. However, the connections between these events and their effects are governed by the fundamental laws of physics, not by magic or mysticism. Appreciating and deciphering these links demands tools of extraordinary sophistication, far beyond simple intuition or storytelling. These cosmic harbingers, arriving in the form of comets and interstellar visitors, carry messages inscribed in the universal language of orbital mechanics and spectroscopic signatures. Yet, before we interpret their significance, we must first decode the more colorful and compelling human narratives that inevitably swirl around such mysterious timing. Narratives shaped by our innate desire for meaning and pattern. This brings us to the most provocative hypothesis of all, the alien hypothesis. It requires not only courage but also scientific rigor to consider seriously. The idea that the interstellar object known as 3I Atlas might be an artificial probe sent by an advanced extraterrestrial civilization raises the possibility that the other comets are part of a coordinated fleet responding to its arrival. While this notion ventures far beyond the boundaries of conventional astronomy into the realm of speculation, it remains within the domain of scientific inquiry. The implications of such a scenario are profound enough that dismissing it outright, without thorough investigation, would be unscientific. To explore this possibility responsibly, we must examine what a truly artificial origin would entail, grounded firmly in the established principles of physics rather than science fiction fantasies. An engineered object capable of traversing interstellar distances would face challenges that are staggering by our current technological standards. It would need to solve the monumental problems of propulsion, covering light years in space, navigation with astonishing precision over spans of millions of years, and communication across the vast emptiness of space, spanning light years. The energy requirements alone are beyond human comprehension. Propelling even a modest probe to the velocities necessary for such journeys demands power sources that dwarf what we possess today. Concepts like nuclear pulse propulsion, antimatter engines, or even physics yet undiscovered would be necessary to achieve the speeds that make interstellar travel feasible within human or even hypothetical extraterrestrial timeframes. Navigation presents no less daunting a challenge. Yet the trajectory of 3I Atlas demonstrates an extraordinary level of precision, aimed at our solar system from potentially hundreds of light years away. Such accuracy presupposes a detailed knowledge of stellar positions and motions over vast geological timescales, implying observational capabilities and computational resources far surpassing our own. It suggests a civilization with the capacity to map the galaxy with remarkable detail, predicting stellar movements long before their craft set out. While these challenges are formidable, they do not violate the known laws of physics. It is conceivable that an advanced civilization, wielding technology beyond our current understanding, might develop methods to overcome these obstacles, applying principles of physics in ways we can only imagine, perhaps through brute force computation or novel propulsion methods. The crucial question, then, is not whether such probes are theoretically possible, rather whether 3I Atlas displays characteristics that could distinguish it as an artificial object rather than a natural one. Spectroscopic analysis offers our most direct and reliable tool for this purpose. Natural comets typically exhibit emission lines associated with water ice, carbon compounds, and simple molecules, substances that form readily in the cold outer regions of stellar systems. If, upon detailed spectroscopic examination, the composition of 3I Atlas reveals signatures of synthetic or manufactured materials, that would be compelling evidence of artificial origin. Conversely, if its spectral fingerprints match those of natural comets, dominated by common molecules like water vapor, carbon monoxide, or methane, the case for artificiality weakens considerably. In essence, the investigation hinges on whether the physical and chemical signatures of this interstellar visitor differ from what we expect from naturally formed celestial bodies. While the engineering feats required to produce an artificial probe capable of interstellar travel are immense, they are not outside the realm of possibility for an advanced civilization. Our task is to scrutinize the data with the utmost rigor, remaining open to extraordinary findings while adhering strictly to scientific standards. Only through meticulous analysis can we hope to distinguish between a natural visitor and an engineered artifact, if indeed such a distinction is even meaningful in this context. Artificial probes, if they exist within our solar system, could harbor materials that are not naturally found in the environments where comets typically form. These might include manufactured alloys, refined metals, exotic composites, or synthetic substances crafted through advanced technological processes. When we analyze the spectrum of 3I Atlas with sufficient spectral resolution and detail, it should reveal crucial clues about its true nature. Specifically, the spectral fingerprint can indicate whether its chemical makeup aligns with what we expect from naturally occurring cometary material, composed mainly of water ice, simple organic molecules, and common minerals, or whether it contains anomalous signatures that hint at artificial origin. The presence of substances that are clearly manufactured, such as refined metals or synthetic compounds, would serve as compelling evidence supporting the hypothesis that this object was engineered rather than naturally formed. Conversely, a spectrum consistent solely with known natural comet compositions would strongly argue against an artificial construction. Behavioral analysis offers another promising approach. Natural comets typically follow ballistic trajectories, their paths dictated predominantly by gravitational forces exerted by the Sun, planets, and other bodies, with minor deviations caused by outgassing. Outgassing occurs when solar heat causes volatile materials within the comet to vaporize, producing small but measurable thrust effects that gradually alter the comet's course. An artificial probe, however, might demonstrate signs of active control, such as course corrections, attitude adjustments, or maneuvering thrusters, that would suggest deliberate navigation rather than passive response. Examining the orbital elements of 3I Atlas reveals no evidence of non-gravitational perturbations beyond what could be attributed to natural outgassing. Its trajectory appears consistent with a passive object simply obeying the known laws of physics. That said, subtle control inputs might be below our current detection thresholds, especially if the craft was meticulously designed to mimic natural cometary movement, employing minimal or undetectable thrusters with precise timing. The most definitive test for artificial origin likely lies in communication signatures. Operating probes would probably maintain some form of contact with their creators or control systems through radio transmissions, laser pulses, or other electromagnetic signals. Such signals might be detectable by terrestrial radio telescopes or optical observatories equipped for electromagnetic monitoring. The Search for Extraterrestrial Intelligence, SETI, has established protocols for analyzing signals, aiming to distinguish artificial transmissions from natural astrophysical sources. Systematic monitoring of 3I Atlas across multiple frequency bands has so far detected no obvious artificial signals. However, the analysis continues as the object draws nearer to Earth, because advanced civilizations could employ communication methods we have yet to conceive or operate on frequencies outside our current monitoring range. The absence of detected signals thus far does not conclusively rule out artificial origin, but it does set constraints on possible communication strategies. The hypothesis of coordination, suggesting that our 7 traditional comets might be some form of engineered fleet responding to the arrival of 3I Atlas, enters even more extraordinary territory. Such a scenario would require each member of the swarm to possess its own propulsion and navigation systems capable of precise, independent maneuvering. These craft would need to be coordinated to arrive within a narrow window of time, despite being launched from potentially different locations across interstellar distances and traveling through space for thousands of years. The logistics of such a complex, synchronized operation challenge human imagination, as it implies a level of technological sophistication and strategic planning far beyond current human capabilities. The idea of multiple objects launched independently from separate points, carefully timed to converge in our solar neighborhood after journeys spanning millennia, entails an extraordinary level of engineering, foresight, and interstellar coordination, an idea that stretches the limits of plausibility under our current understanding of physics and technology. The orbital profiles of our 7 well-documented comets exhibit unmistakable signatures indicative of their origins within our solar system. Their chemical compositions align closely with the expected patterns observed in objects formed in the distant reaches of our planetary neighborhood. Furthermore, their discovery histories, carefully recorded by established survey programs that have monitored these objects over many years or even decades, corroborate their natural provenance. Their trajectories, meticulously calculated and continuously tracked, show no signs of artificial interference such as course corrections or coordinated maneuvers that would suggest external manipulation. If by some hypothetical scenario these objects were indeed artificial constructs, they would have to be extraordinarily sophisticated in their camouflage. To convincingly mimic genuine solar system comets, such deception would require detailed knowledge of our astronomical capabilities and observational expectations. This would imply a level of surveillance and analysis far beyond what their apparent technological demonstrations suggest, capabilities that would be necessary for an entity attempting to conceal artificial origin under the guise of natural objects. The most compelling argument for some form of coordination among these objects lies in the timing correlation of their arrivals, particularly involving 3 of the comets, what we might call the 3I Atlas objects, within the swarm. Although the specific mechanism behind this apparent synchronization remains elusive, the pattern itself is striking. Statistical analysis of the comet arrival patterns could reveal whether the clustering observed in 2025 is truly anomalous, exceeding what random distribution and natural variation would produce. However, when evaluated solely on timing, this correlation offers only weak evidence for intentional artificial coordination. This is especially true when considering the broader context. The continual enhancement of sky survey technologies and the natural variability in comet discovery rates. The proliferation of automated wide-field sky surveys has dramatically increased our ability to detect objects that might have previously gone unnoticed or untracked for decades. This technological advancement naturally elevates the likelihood of observing clusters or patterns, sometimes coincidental, that would have been statistically improbable in the past. The human tendency to seek explanations involving alien intelligence is deeply rooted in psychological needs, an innate desire to find purpose and agency behind seemingly random or coincidental events. When faced with unusual alignments or bursts of activity, we instinctively prefer explanations invoking intelligent design or external agency rather than accepting pure chance. This cognitive bias is reinforced by contemporary anxieties about humanity's cosmic isolation and the limitations of our current technology, implying that if advanced civilizations are capable of visiting or influencing our solar system, it suggests that we are not alone and that technological prowess beyond our own is possible. Nevertheless, such extraordinary claims demand extraordinary evidence. The burden of proof rests squarely on those proposing an artificial or alien origin, requiring clear, observable characteristics that withstand rigorous skeptical scrutiny. Presently, the available observational data, spectroscopic analyses, trajectory calculations, and discovery records do not provide sufficient evidence to support the hypothesis that either 3I Atlas or any member of the comet swarm is artificial in origin. While it remains theoretically possible that highly sophisticated camouflage operations could perfectly imitate natural objects, such scenarios involve assumptions about alien capabilities and motives that extend well beyond the limits of current knowledge and evidence. The investigation into this phenomenon continues with the hope that future, more detailed observations, obtained through improved instrumentation or targeted follow-up, may uncover features or signatures that current analyses have yet to detect. Until then, the evidence-based stance remains that these comets are most plausibly natural, arising from well-understood processes within our solar system, with their clustering attributable to the increasing sensitivity of our detection methods rather than deliberate external control. As these celestial visitors draw nearer, our ability to conduct more detailed spectroscopic analyses, utilize higher resolution imaging, and deploy more sensitive searches for artificial signals or behavioral anomalies will be significantly enhanced. Such advancements in observational technology and methodology allow scientists to scrutinize these objects with unprecedented precision, increasing the likelihood of detecting any genuine signs of artificial origin should they exist. The world's leading professional astronomers approach these investigations with appropriate skepticism concerning exotic explanations, recognizing the importance of rigorous, systematic observation and analysis. Through disciplined application of the scientific method, they aim to differentiate between mere wishful thinking and legitimate, evidence-based discoveries. This framework provides the essential tools for distinguishing truly anomalous phenomena from natural occurrences, ensuring that claims of artificiality are substantiated by robust, reproducible data. The quest to detect extraterrestrial intelligence stands as one of the most profound and consequential inquiries confronting humanity. Should conclusive evidence arise, such as indications that 3I Atlas or any associated objects exhibit unmistakable artificial characteristics, such a discovery would fundamentally alter our understanding of our place within the cosmos. It would challenge existing paradigms and open new horizons of scientific and philosophical exploration. However, until such evidence surpasses the stringent standards required to persuade even the most skeptical scientists, criteria that demand clear, reproducible, and peer-validated data, the alien hypothesis remains within the realm of speculation, not established fact. While the possibility of extraterrestrial intelligence continues to inspire wonder and curiosity, current observations favor conventional explanations rooted in natural astrophysical processes. Still, it is crucial to maintain a balance, embracing curiosity about extraordinary possibilities without abandoning the disciplined rigor of scientific inquiry. The universe has a long history of surprising us with phenomena that at first appeared impossible, only to be later understood as natural effects or cosmic coincidences. Turning to the most ominous interpretations, the so-called doomsday scenario presents a stark and foreboding vision of the year 2025. In this darkest projection, the convergence of our 7 cometary visitors is perceived as a harbinger of civilization-threatening catastrophe, orchestrated by forces beyond human comprehension or control. This narrative transforms the mechanics of celestial motion into a form of cosmic warfare, where ice and rock are weaponized to bring about human extinction. Such scenarios, while gripping as fiction, demand careful and honest evaluation grounded in scientific reality. The actual risk of impact from these objects is governed by well-understood physics, enabling precise calculations of collision probabilities and potential consequences. In reality, none of our 7 cometary travelers, namely Pan-STARRS, SWAN, Stereo, Atlas K1, Atlas G3, Lemon, and Neat, pose any threat of collision with Earth during their current approaches. These objects maintain safe distances measured in millions of kilometers, placing them well beyond the zone where gravitational influences could precipitate catastrophic encounters. For instance, the trajectory of 3I Atlas follows a hyperbolic path, ensuring it will pass safely by all major solar system bodies, ultimately slinging it back into interstellar space without returning. Such orbital mechanics operate with a precision that leaves little room for ambiguity regarding potential impact risks, reaffirming that current observations do not support any imminent threat to our planet. Interstellar objects, due to their high velocities and hyperbolic trajectories, actually lower the likelihood of colliding with solar system bodies rather than increasing it. Since objects moving at such speeds cannot be gravitationally captured, meaning they cannot settle into stable orbits around the Sun, their potential to impact our planetary neighborhood is minimal. This absence of impact risk, therefore, does not eliminate all concerns associated with such visitors, especially when considering other types of hazards. One significant area of concern involves space weather phenomena driven by our star's solar maximum, the period of peak solar activity in its approximately 11-year magnetic cycle, which is predicted to reach its most intense phase in 2025. During this time, the Sun's magnetic field becomes highly turbulent, unleashing solar flares, coronal mass ejections, and energetic particle streams that can have profound effects on our technological infrastructure. Power grids, satellite communication networks, and navigation systems all become vulnerable when bombarded by these charged particles, risking widespread disruptions. Importantly, these risks are fundamentally rooted in the Sun's activity rather than the behavior of comets or other celestial visitors. The timing of this heightened solar activity is independent of any incoming cometary objects. It is a natural cycle that repeats every 11 years, reaching its climax in 2025 regardless of external factors. The observed correlation between active comets and solar maximum conditions simply reflects a shared response to broader solar system dynamics, rather than any causal influence of comets on solar behavior. To accurately assess the real level of threat, scientists rely on rigorous statistical analysis that distinguishes genuine dangers from coincidental clusterings of low-probability events. Human pattern recognition, especially when faced with multiple seemingly related phenomena happening simultaneously, has a tendency to overestimate the likelihood of coordinated threats. Our brains are wired to seek explanations, often interpreting random alignments as meaningful, particularly when multiple improbable events occur at once. Professional risk analysis employs sophisticated mathematical frameworks designed to account for the multiple comparisons problem, where evaluating many potential correlations increases the chances of finding spurious patterns. When scientists test numerous possible relationships between different types of events, some patterns will inevitably appear purely by chance, without any underlying causal connection. Recognizing this, analysts apply methods to quantify the likelihood that observed correlations are random, thereby avoiding false conclusions. The so-called doomsday scenario, where a series of low-probability events like a comet swarm and an interstellar visitor combine to threaten civilization, tends to gain psychological traction precisely because it consolidates multiple unlikely phenomena into a singular threatening entity. This mental bundling amplifies perceived risk, presenting a narrative that demands urgent concern and preparedness. Yet orbital mechanics, the fundamental laws governing celestial motion, do not support such artificial bundling. Each object in our solar system follows its own trajectory, dictated by gravitational forces acting independently. The appearance of coordinated activity is a product of human perception and timing, not genuine physical interaction. Historical records offer perspective on how extraordinary astronomical events have been linked in the collective imagination to terrestrial disasters. Bright comets, for instance, have appeared during times of war, plague, famine, and social upheaval. However, detailed statistical analysis shows no meaningful correlation between comet appearances and an increase in human catastrophes. The perception of a connection often arises because societies tend to focus more intently on dramatic celestial phenomena during periods of already high stress, amplifying the impression that these events are linked, when, in fact, they are not. Throughout human history, narratives crafted in times of turmoil tend to highlight extraordinary phenomena that seem connected to ongoing struggles, often magnifying their significance in the collective consciousness. Conversely, during periods of peace and stability, similar celestial events tend to fade into the background, attracting little to no historical notice. Today, our civilization faces genuine existential threats, risks that demand serious attention and strategic action. Issues such as nuclear conflict, the accelerating impacts of climate change, global pandemics, and rapid technological disruptions pose tangible dangers to our collective well-being. These threats are rooted in mechanisms that we understand well. They can be analyzed through scientific methods modeled with precision and addressed effectively through appropriate policies, preparedness, and international cooperation. In stark contrast, the so-called doomsday comet scenarios serve as distractions that divert focus from these genuine problems. By emphasizing threats that pose minimal real danger, often exaggerated or speculative, such narratives divert precious resources and attention away from critical issues. Misallocating our time and efforts toward imaginary catastrophes undermines our capacity to confront actual challenges that require sustained, coordinated action. It is vital that claims about cosmic threats, particularly those suggesting imminent global catastrophe, meet rigorous standards of evidence. Vague assertions, especially those pointing to suspicious timing or coincidence, are insufficient. When discussions arise about whether our current comet swarm could threaten civilization, they must be anchored in specific scientifically grounded mechanisms. Quantified probabilities, detailed models, and independently verifiable data are essential to substantiate such claims. The scientific method remains our most reliable tool for assessing these possibilities objectively. Through hypothesis testing, rigorous statistical analysis, and peer review, we can distinguish legitimate concerns supported by evidence from unfounded fears rooted in cognitive biases or wishful thinking. Moreover, our advanced space monitoring agencies employ sophisticated systems designed to track genuine space weather hazards. Solar storms, cosmic radiation, and other phenomena that have the potential to impact critical infrastructure. These systems are capable of detecting and issuing warnings about real threats long before they materialize, providing crucial lead time for mitigation. The absence of any official alerts or warnings from these agencies regarding increased comet activity or solar maximum conditions strongly suggests that the risks of imminent technological collapse are negligible. Expert risk assessors equipped with the most comprehensive observational data have found no indication of extraordinary threats that would warrant emergency measures. Public education on actual space weather risks plays a crucial role in maintaining a balanced perspective. It helps prevent unnecessary panic and ensures that society remains focused on genuine hazards, rather than sensationalized or speculative scenarios. While solar storms can indeed pose risks to our technological systems, disrupting satellites, power grids, and communication networks, these threats are well understood. Their mechanisms are predictable, and effective strategies for monitoring and mitigation are in place. The upcoming period of increased comet activity in 2025 promises both spectacular opportunities for astronomical observation and valuable scientific insights into the dynamics of our solar system. These benefits far outweigh any minimal risks associated with the observational processes. Ultimately, the greatest danger lies in allowing unfounded fears to overshadow legitimate scientific curiosity and educational endeavors. Emphasizing evidence-based understanding ensures that our efforts remain focused on addressing real challenges, advancing knowledge, and fostering resilience against genuine threats, rather than succumbing to alarmist narratives that diminish our capacity to respond effectively. Responsible science communication demands a candid acknowledgement of the uncertainties inherent in our understanding, while maintaining a balanced perspective regarding the scale of genuine risks. When we openly admit that certain aspects of our ongoing comet investigation remain elusive or unexplained, it is crucial to emphasize that such gaps in knowledge do not automatically imply imminent danger or threat. The universe has a long history of producing phenomena that challenge our current scientific frameworks, events that stretch the boundaries of our understanding. Yet these occurrences rarely, if ever, pose immediate risks to human civilization. Progress in science hinges on systematically exploring these phenomena, approaching them with curiosity and rigor, and resisting the temptation to leap to premature conclusions based on incomplete data or cognitive biases. As we stand on the brink of examining some of the most intricate and elaborate conspiracy theories woven by human imagination around this unusual year of comet activity, it is vital to remember that extraordinary claims, such as those suggesting cosmic threats, demand equally extraordinary evidence before they can be taken seriously. Misinformation and fear-driven speculation serve no constructive purpose when they are divorced from meticulous analysis rooted in actual probabilities and well-understood mechanisms. In fact, the so-called doomsday scenarios often reveal more about human psychology than about the underlying physics of the cosmos. Our innate pattern-seeking instincts, developed over millennia, tend to interpret clustering of rare events as signs of coordinated threats, especially during times of societal stress when people are actively searching for explanations to soothe their anxieties. Yet, it's essential to recognize that the universe operates independently of our fears and expectations, following laws of physics that are indifferent to human concerns. Comets, for instance, adhere to gravitational trajectories that can be calculated with remarkable precision. Solar activity governed by magnetic cycles can be statistically predicted, and space weather effects, resulting from electromagnetic interactions, are measurable and modelable through well-established principles. The universe's clockwork, as it were, continues its precise and predictable operation regardless of the dramatic narratives we may craft to explain its most visible phenomena. Understanding and accepting this natural order offers both practical benefits, such as accurate forecasting, and a profound sense of reassurance that transcends the fleeting thrill of sensationalized doomsday scenarios. It reminds us that the universe, in its vast complexity, remains comprehensible when approached with scientific discipline. Part 14. The Invasion in Disguise. Among the most elaborate and sensational conspiracy theories about our seven-comet swarm is the idea that we are witnessing the early stages of an extraterrestrial invasion, cleverly disguised as natural celestial phenomena. According to this hypothesis, the interstellar object known as 3I Atlas acts as a command vessel, orchestrating a fleet of objects that mimic ordinary comets while secretly conducting reconnaissance and preparing for eventual colonization or occupation of our solar system. Such a scenario demands technological capabilities that are staggering by human standards, implying a level of sophistication that far exceeds our current understanding. For this conspiracy to hold, each purported probe would need to possess camouflage techniques advanced enough to replicate the spectroscopic signatures, outgassing behaviors, and orbital characteristics typical of genuine solar system comets. This level of deception would necessitate an intimate knowledge not only of our astronomical methods but also of the physical behaviors that characterize natural comets under solar heating conditions. The engineering challenges involved in creating artificial objects capable of fooling our most sophisticated instruments, spectrometers, telescopes, and remote sensing systems, are monumental, requiring materials and technologies that might seem like science fiction. The task of designing these objects to convincingly imitate the subtle signatures of natural celestial bodies involves overcoming significant obstacles in materials science, thermodynamics, and optical detection. Moreover, the complexity of such an operation would be extraordinary. Crafting multiple artificial objects, each with tailored orbital paths, behaviors, and signatures, and deploying them across the vast reaches of interstellar space, all while maintaining the illusion of natural origins. This hypothetical fleet would need to coordinate their appearances and trajectories with near-perfect timing, suggesting a level of planning and technological mastery that challenges our most ambitious engineering visions. Considering the profound engineering and technological demands, the idea of a covert extraterrestrial invasion fleet concealed within a seemingly natural comet swarm stretches the limits of plausibility. Yet it captures the imagination and highlights the importance of rigorous scientific scrutiny when evaluating extraordinary claims. Modern spectroscopic techniques enable scientists to identify molecular species with remarkable accuracy, even distinguishing subtle differences in isotopic ratios. These ratios serve as cosmic fingerprints, revealing the environments in which objects formed and the chemical processes they underwent over eons. Any artificial probe attempting to mimic natural objects within our solar system would need to carry materials meticulously matched to those expected for bodies formed billions of years ago in the distant reaches of our planetary neighborhood. This presents a formidable challenge because the outgassing behavior that creates the distinctive tails of comets, their glowing streams of gas and dust, is rooted in complex processes. Natural comets develop their characteristic appearance through sublimation, where volatile substances within them vaporize under the intense heat of the sun. This sublimation process depends heavily on the comet's internal structure, its specific composition, and thermal properties, traits that evolve over extensive geological timescales. To convincingly imitate this behavior, an artificial object would require highly sophisticated engineering to replicate the precise sublimation patterns and activity levels observed in genuine comets. Light curves, which are the graphical patterns of brightness variation that cometary objects exhibit over time, offer another vital clue in the quest to distinguish natural from artificial origins. Typically, natural comets display smooth, gradual changes in brightness punctuated by occasional outbursts, sudden, dramatic increases in luminosity, when new volatile materials are exposed to solar heating or internal processes. These brightness fluctuations are often tied to the comet's rotation, with the periodicity revealing how the object tumbles or spins, especially if it is irregularly shaped. These rotation periods and brightness patterns serve as signatures of natural, minimally controlled bodies in orbit around the Sun. If our 7 traditional comets were, in fact, artificial constructs, crafted or controlled entities, they might eventually exhibit light curve signatures that set them apart from authentic objects. Specifically, engineered objects could demonstrate artificially controlled rotation, with precisely timed brightness variations that do not align with natural tumbling or spontaneous outgassing. Such signatures of active attitude control, maneuvers designed to adjust or stabilize orientation, would be detectable through sustained high-precision photometric monitoring over multiple observation cycles. The most profound challenge in camouflage, however, lies in the orbital characteristics of these objects. Natural comets follow trajectories that are shaped over millions of years by gravitational interactions, planetary encounters, and perturbations within the solar system. Their orbital histories can be traced backward through extensive dynamical calculations, revealing signatures of their likely formation regions, such as the outer Oort cloud or the Kuiper belt. These histories carry the fingerprints of their origin, regions, encounters, and perturbations that are difficult for artificial objects to replicate convincingly over geological timescales. To produce artificial objects with orbital paths indistinguishable from those of genuine solar system bodies, an invader would need to launch them from precise locations and directions, ensuring their current trajectories align with the expectations for objects formed in specific regions of the outer solar system. Such a feat would involve extraordinary logistical complexity, crossing interstellar distances and spanning millions of years of orbital evolution, an undertaking that stretches human comprehension. Moreover, the discovery records of these objects, particularly those like Comet 7 or Neat, Lemon, and others surveyed by well-documented programs, are detailed. These surveys have meticulously logged the circumstances of their detection, including the conditions, timing, and subsequent orbital calculations derived from decades of observations. If any of these objects were recently arrived artificial constructs rather than long-period comets on natural orbits, their sudden appearance within survey data would likely have triggered immediate and intense scrutiny by astronomers specialized in orbital analysis. Such a rapid and unexpected detection would raise eyebrows, prompting rigorous investigations into their orbital histories, trajectories, and physical properties. In essence, the existing detailed records and the natural dynamical signatures embedded in their orbits form a robust framework that makes artificial origins, especially recent arrivals, highly unlikely without leaving detectable anomalies. The lack of any alerts or warnings from current observational systems strongly suggests that scenarios involving recently launched artificial objects, designed to mimic natural comets, are highly unlikely. If an organized extraterrestrial invasion fleet were covertly operating within our solar system, it would necessitate constant high-bandwidth communication among multiple dispersed entities, including the 7 autonomous probes in a central command vessel. Such coordination would require frequent exchanges of data via radio transmissions, laser signals, or other electromagnetic methods, signals that terrestrial monitoring networks could potentially detect or intercept. In fact, our existing search efforts for extraterrestrial intelligence, conducted by sophisticated radio telescopes and monitoring arrays, are specifically designed to scan large swathes of the sky for signs of artificial signals. Programs like Breakthrough Listen, along with observatories such as Arecibo and others around the world, systematically seek out the very kinds of communication patterns that would be necessary for a coordinated fleet operating across vast distances. The persistent absence of any such artificial signals associated with our comet swarm does not entirely rule out the possibility of covert communication, as advanced civilizations might employ methods beyond our current detection capabilities. Nonetheless, the sheer strength, repetition, and patterning of signals needed to sustain fleet-level coordination across the solar system would likely produce detectable signatures with today's instruments. From a strategic perspective, the notion of a disguised invasion poses significant questions about feasibility and efficiency. Why would an advanced interstellar civilization invest enormous resources into elaborate deception, deploying multiple probes and a command vessel, when a direct approach or simpler reconnaissance methods would achieve their goals more effectively? Camouflage and stealth are costly, and their strategic value diminishes if the target civilization has no effective means of defense against more straightforward detection or countermeasures. The resource expenditure required to produce and deploy 7 highly sophisticated camouflage probes, along with a central command ship, would surpass the total economic output of human civilization by vast margins. Civilizations capable of interstellar travel, possessing technology far beyond ours, would likely have the means to conduct reconnaissance without such complex subterfuge, rendering deception unnecessary or strategically irrelevant. Moreover, the current behaviors of our comet swarm, especially the trajectory of 3I Atlas, destined to exit our solar system forever, are inconsistent with the goal of establishing a permanent presence or invasion. Such an object's departure trajectory indicates it is a transient visitor, not a vessel designed for occupation or long-term infiltration. The prevalence of invasion scenarios in popular speculation often stems from contemporary anxieties about rapid technological change, resource depletion, and the perceived loss of human sovereignty. These fears tend to project human concerns about dominance and conflict onto the cosmos, especially when confronted with phenomena that seem to operate beyond our full understanding. However, all such speculation falls short of empirical support. The observed objects, including our interstellar visitor, show no capabilities beyond what is expected of natural bodies, exhibiting no signs of active control, advanced technology, or behavior indicative of deliberate deception. In essence, while the idea of an elaborate extraterrestrial conspiracy is compelling in fiction and popular imagination, the actual evidence, absence of signals, realistic trajectories, and known physical properties, strongly favors natural explanations. Until definitive signs of artificiality emerge, the simplest, most scientifically consistent interpretation remains that these objects are natural remnants, products of cosmic processes far exceeding our current technological reach, but entirely consistent with known physics. The hypothesis of an invasion suggesting extraterrestrial intervention or hostile intent demands concrete evidence of artificial traits, coordinated actions, or threatening capabilities in the objects under scrutiny. It cannot rest solely on the absence of proof that these objects are purely natural. Rather, it requires positive, verifiable signs indicating deliberate engineering or purposeful control. At present, the comprehensive observational data collected on our comet swarm offers no support for such an artificial origin. Spectroscopic studies, analyses that reveal the chemical makeup of these objects, consistently show compositions aligned with natural formation processes in our solar system's environments. Their orbital paths, when examined in detail, conform to expectations for objects that have evolved under gravitational influence over millions of years, following trajectories shaped by the known laws of physics. Furthermore, behavioral patterns, such as brightness variations, tail development, and movement, show no evidence of active manipulation, control, or coordination that would indicate external influence beyond what statistical chance might produce. The responsibility of proving artificiality lies firmly with those proposing extraordinary claims. Such proponents must present compelling evidence of engineered characteristics or coordinated behavior that withstands rigorous scrutiny and skepticism. Merely noting the absence of evidence for artificial traits is insufficient. It does not prove that such a scenario is impossible. Instead, current data and analysis favor conventional, well-understood astronomical explanations rather than exotic or speculative ones involving alien intervention or orchestrated fleets. Professional astronomers and space scientists maintain systematic and vigilant monitoring of all unusual objects, precisely to detect any anomalies that could suggest an artificial origin. These protocols are designed to differentiate between natural phenomena and potential extraterrestrial artifacts, applying strict standards of evidence to separate legitimate scientific discoveries from unfounded speculation. As observational technologies improve and closer approaches are made, the capacity to analyze these objects in greater detail also increases. Any genuine artificial signatures, if they exist, should become more conspicuous with enhanced resolution, spectral data, and behavioral monitoring, providing clearer clues as to their true nature. While science fiction scenarios serve valuable roles in exploring theoretical possibilities and preparing us for the unexpected, they should not be mistaken for scientific fact. The entertainment value of such ideas might inspire imagination, but it does not justify presenting them as credible conclusions without supporting evidence. Currently, the evidence does not justify extraordinary claims of alien invasion or deliberate interference. The universe already presents enough profound mysteries and intriguing phenomena that warrant investigation without inventing additional puzzles driven by wishful thinking or fear-based speculation. Our 7-comet swarm, intriguing as it is, a statistically significant clustering of objects, merits thorough scientific inquiry. However, this investigation must be grounded in evidence and grounded in the scientific method, rather than assumptions or preconceived notions about extraterrestrial agendas. As we continue our research, synthesizing data and refining our understanding, it's vital to uphold the standards of scientific rigor without sacrificing the sense of wonder that drives curiosity about the cosmos. The tools of empirical investigation, spectroscopy, orbital analysis, behavioral monitoring, are our best means of distinguishing genuine discoveries from mere speculation. They have the power to reveal phenomena that challenge our current understanding, but only if we approach them with disciplined observation and cautious interpretation. The universe, in its vast complexity, still holds surprises that may someday force us to revise long-held assumptions. These revelations will come not from leaps of imagination or unfounded conjecture, but through meticulous study and careful analysis of the evidence at hand. For now, our current understanding supports the view that the mysteries of our cosmic environment are best approached with scientific humility and a commitment to truth. The universe's genuine enigmas, hidden in the behavior of distant objects or the subtle signatures of interstellar visitors, await discovery through the diligent application of our best scientific tools. And so the investigation continues, guided by curiosity, disciplined by skepticism, and ever mindful that the most extraordinary truths are revealed not through speculation, but through the unwavering pursuit of evidence. The message carried by this celestial swarm resonates with both wonder and scientific rigor. After months of meticulous investigation, carefully tracking orbital mechanics, analyzing the probabilities through rigorous statistical methods, and scrutinizing every plausible connection between the interstellar visitor, 3I Atlas, and the 7 comets that have graced our skies, an outcome emerges that is both reassuring and profoundly remarkable. The evidence points not to some exotic form of coordinated activity or extraterrestrial intervention, but to a natural, majestic phenomenon. The clustering of these 7 comets in the year 2025 exemplifies genuine statistical grouping, a rare occurrence that commands attention precisely because such concentrations are so infrequent that they feel imbued with meaning. Each of these comets, Pan-STARRS, Swan, Stereo, Atlas K1, Atlas G3, Lemon, and Neat, follows its own independent orbital journey crafted by the timeless influence of gravity. These trajectories were set in motion millions of years ago, long before human civilization emerged to witness their eventual convergence. This fact alone underscores the natural origins of what appears to be a remarkable alignment. To dismiss this convergence as mere coincidence, however, would be to overlook the profound beauty and the invaluable scientific insights embedded within this cosmic event. What we are observing is a celestial festival, orchestrated by the universe itself, a spectacle that offers unprecedented opportunities for comparative comet studies, public engagement with astronomy, and a deeper understanding of the dynamics governing the outer solar system. The timing of this gathering may be entirely natural, yet its impact, scientifically and culturally, is anything but ordinary. Adding to the wonder is the presence of 3I Atlas, our solar system's first well-documented interstellar visitor that exhibits unmistakable comet-like behavior. This object, originating from beyond the bounds of our solar neighborhood, carries with it ice and dust formed around a distant star, material that has been seasoned by millions of years of interstellar travel. As it ventures close to our sun, this ancient alien relic begins to vaporize, revealing a tale of cosmic chemistry that makes the unfamiliar familiar. A story told through telescopes worldwide, making the chemistry of distant worlds visible to human eyes. The temporal correlation between the arrival of 3I Atlas and our most active comet year in recent memory continues to captivate researchers. While current evidence suggests that this is a coincidence rather than a direct causal link, the pattern itself remains intriguing. Sometimes the universe arranges what we might call meaningful feeling patterns, apparent correlations that emerge purely through natural processes without any underlying intent. These patterns remind us that coincidence and significance can coexist harmoniously, without the need for mysterious explanations. Our thorough investigation reveals no orbital relationships, behavioral anomalies, or timing correlations that exceed what statistical analysis would predict for objects influenced solely by known forces, gravity and solar heating. Each comet's origin story is unique. Its formation in the distant reaches of the solar system, the gravitational perturbations that nudged it into its current orbit, and its responses to the increasing heat as it approaches perihelion. This careful conclusion does little to diminish the excitement surrounding the celestial activity of 2025. On the contrary, it opens up a landscape of scientific opportunity. The simultaneous appearance of multiple bright comets allows researchers to compare how different compositions, sizes, and orbital geometries respond to the same solar environment, an unprecedented natural laboratory. Such comparative studies deepen our understanding of comet physics in ways that isolated observations cannot provide, enriching our knowledge base and inspiring further inquiry into the mysteries of the outer solar system. The heightened solar activity associated with the peak phase of the solar cycle promises to dramatically intensify the visual display of our ongoing comet parade, transforming it into a spectacular cosmic spectacle visible even to the casual observer. Simultaneously, this period offers a unique window for natural experiments in space weather physics, as the same intense solar phenomena, particularly coronal mass ejections, pose risks to our technological infrastructure while producing the very conditions that generate the most striking comet tails and plasma disturbances. These solar storms can cause sudden tail disconnections and plasma instabilities in comets, phenomena that not only create breathtaking visuals for astrophotographers but also serve as invaluable data points for scientists studying the sun's influence on the solar system. Across the globe, amateur astronomers are meticulously documenting this celestial festival with unprecedented detail. Their collective efforts are building extensive photographic archives that will serve the scientific community for decades, offering insights into comet behavior, tail formation, and space weather effects. The democratization of high-quality astronomical imaging, enabled by advances in affordable telescopic equipment and digital technology, means that hundreds of dedicated observers are contributing valuable data. This crowdsourced approach greatly enhances our observational capacity, supplementing and expanding upon the work of professional monitoring programs and allowing for a broader, more nuanced understanding of these transient phenomena. The public engagement sparked by our investigation into the 7 comets exemplifies how extraordinary astronomical events can ignite widespread interest in space science and foster critical thinking skills. As citizens analyze and interpret these phenomena, they participate in a scientific process, evaluating extraordinary claims against available evidence that transcends traditional outreach methods. This approach not only educates but also demonstrates how the scientific method helps distinguish between well-founded facts and speculative hypotheses, reinforcing the importance of evidence-based reasoning. While the absence of any signs of extraterrestrial intervention or artificial influence might seem to close certain avenues of inquiry, it certainly does not eliminate all possibilities for future discoveries. Continued monitoring remains essential, as subtle correlations or anomalies, currently below our detection thresholds, could emerge with improved measurement techniques or as objects approach closer. Scientific progress often hinges on incremental improvements in observational accuracy, analytical methods, and data interpretation, which have a remarkable capacity to reveal phenomena previously hidden from view. The statistical clustering of comet arrivals in the year 2025 invites further investigation into the long-term dynamics of our solar system. If similar patterns have appeared in the past or are expected to recur in predictable cycles, they could reflect underlying processes such as gravitational resonances, influences from the solar cycle, or other periodic forces operating over astronomical timescales. Understanding these influences could shed light on how cometary populations are modulated over millions or billions of years, offering clues about the long-term stability and evolution of our planetary neighborhood. Professional astronomers will maintain vigilant and systematic observation of all unusual objects within our solar system, diligently analyzing their trajectories, compositions, and behaviors. They remain alert for signs indicating potential artificial origins or exotic physical phenomena, applying rigorous evidentiary standards to differentiate genuine anomalies from natural statistical fluctuations. This disciplined approach ensures that extraordinary hypotheses, whether proposing artificial intervention or other unconventional influences, are assessed with scientific integrity and skepticism. Beyond the immediate questions surrounding the Interstellar Visitor 3 Atlas and its potential connections to the local comet swarm, this investigative process exemplifies how rigorous scientific inquiry can address even the most speculative hypotheses without succumbing to the allure of sensationalism. In an era where social media algorithms often accelerate the viral spread of sensational claims, maintaining a careful balance between curiosity and skepticism is more vital than ever. It is essential to prioritize evidence and methodical analysis over conjecture, ensuring that our understanding of cosmic phenomena remains rooted in scientific rigor rather than the transient whims of popular fascination. The responsibility of the scientific community extends beyond merely disseminating accurate information. It also requires a steadfast commitment to honestly acknowledging uncertainties, avoiding the temptation to overshadow factual integrity with sensationalized claims or premature conclusions driven by entertainment. The celestial spectacle of the comet swarm in the year 2025 exemplifies how human psychology, particularly our innate pattern-seeking tendency, can transform objective astronomical phenomena into compelling yet subjective narratives about cosmic significance. This process, while not inherently problematic, demands a conscious effort to clearly differentiate between empirical observations and the interpretive stories we craft around them. Modern astronomy equips us with unprecedented tools and techniques capable of reliably distinguishing between genuine anomalies, those phenomena that defy current understanding, and apparent patterns that naturally emerge from the inherent randomness of statistical variation. These advanced instruments and analytical methods reveal phenomena on a cosmic scale that often surpass the limits of human imagination, doing so without resorting to exotic or speculative explanations. Instead, they demonstrate that the universe's complexity and beauty frequently exceed even the most creative human conjectures, affirming that reality itself can be more astonishing than any story we invent. As this investigation draws to a close, we are left with a universe that is simultaneously more understandable and more enigmatic than popular narratives tend to suggest. It operates according to immutable physical laws, laws that are accessible through meticulous observation and scientific inquiry. Yet these same laws produce phenomena that often challenge our intuition, inspiring us to continue exploring, questioning, and expanding our understanding of the cosmos. The overarching lesson of the 2025 comet swarm may ultimately be that the universe offers enough authentic wonder on its own, without the need to invent additional mysteries. The mere convergence of 7 independent comets, each following natural trajectories shaped over millions of years, alongside a rare interstellar visitor making its only pass through our solar system, stands as a remarkable cosmic coincidence deserving of celebration in its own right. This extraordinary event also holds profound educational value, extending far beyond the realm of astronomy. It serves as a catalyst for developing critical thinking skills applicable across all fields of human knowledge. Skills such as discerning between correlation and causation, rigorously evaluating claims against appropriate evidence standards, and maintaining a sense of wonder while demanding scientific rigor. Cultivating these intellectual tools equips society not only to understand celestial phenomena, but also to navigate the complexities of information in an increasingly interconnected world. Looking ahead, future generations may look back on the year 2025 as a pivotal moment, a watershed, when advancements in survey technology coupled with the proliferation of social media transformed routine astronomical discoveries into cultural phenomena. These widespread engagements sparked global conversations about evidence, probability, and the very nature of scientific knowledge, making the universe's mysteries accessible to millions and fostering a deeper appreciation for the scientific process. Ultimately, the message conveyed by this celestial parade may be that human curiosity, combined with our capacity for analysis and understanding, constitutes the most extraordinary achievement of this entire episode, far more than any hypothetical cosmic coordination or alien intervention. Through the development of sophisticated tools capable of detecting interstellar visitors, calculating orbital parameters with incredible precision, and rigorously evaluating extraordinary claims through statistical analysis, we have reached a level of scientific maturity that deserves recognition alongside the awe-inspiring phenomena we observe. This fusion of technological prowess and intellectual rigor exemplifies our ongoing journey toward understanding the universe, not through fanciful stories or unfounded speculation, but through disciplined inquiry and the relentless pursuit of truth. In doing so, we reaffirm that the universe's genuine mysteries provide ample wonder, urging us to look beyond illusions and to appreciate the profound beauty inherent in the natural order of cosmos. The cosmos might not be delivering clandestine messages through orchestrated cometary arrivals, yet it persistently offers us avenues for discovery, opportunities that reward meticulous observation with profound insights into our celestial surroundings. This inquiry circles back to its origins, rooted in a sense of awe inspired by uncanny timing, tempered by a steadfast commitment to rigorous scientific scrutiny, and fueled by a deep reverence for a universe rich with genuine mysteries. These mysteries are enough to captivate human curiosity across countless generations, ensuring that our quest for understanding endures. With hypotheses thoroughly tested and evidence carefully weighed, the spark of wonder remains unblemished, ready to ignite future explorations that reach beyond the limits of our present observational capabilities, beckoning us toward new horizons of cosmic discovery.